the last day of the workshop on string field theory and the related aspects. Welcome to the session. So the first speaker today is Lionel Mason from Oxford. So he's going to tell us about the Twistorial ambitwister strings, part 1, models. So let's...
Okay. So thank you very much for the invitation to allow us to talk about our work. It's a shame that we're not actually there with you and able to chat sort of so freely as we might in physical presence of each other. But anyway, so today what I want to do is talk about, well, the title that you might ask is whatever happened to the twister string? What I want to talk about is the way in which ambitwister strings have sort of picked up the twister string, and it provides a kind of what I'd like to think is a deeper understanding, and it gives you extensions which first of all map more closely onto the conventional string, although there's still a lot of mysteries. So this is joint work with Yvonne Geyer and variously with other people, so with research student Julia Albonico and for the 5-dimensional material with David Skinner. And it also built on a whole bunch of work by Freddie Casciazzo and friends, and the perimeter group with John Schwartz and Matt Heidemann, Song Kao Wen, who came up with some interesting amplitude formulae in 6 dimensions. So okay, so this talk is in 2 parts. So the first part is going to be about string models, ambitwister string models, and the second part will be by Yvonne, and she'll talk about the corresponding amplitude formulae that arise. So I thought I'd start with the take-home messages, really, that first of all, that ambitwister strings do give a wide-ranging generalization of twister strings. I should have had a proviso here that this is really alpha prime equals 0. This is all field theory. This is not full fat string theory with higher massive modes. But nevertheless, the original ambitwister string model that David and I came up with has clear parallels with the standard RNS string. And indeed, sort of almost immediately after Nathan came up with a pure spinor analog, just following similar logic. But the key point here is that the target space is not space-time. It's this space of null geodesics, but complexified, so complex null geodesics. And so this is an idea that can be pursued in higher dimensions beyond the original twister string. And because twister representations of ambitwister spaces exist in all dimensions. So the 2 features are, first of all, the target is different. It's a space of complex null geodesics. And also the way in which space-time fields are encoded is different. We no longer have sort of metrics, connections, and whatnot. Everything somehow is to do with a deformation of complex structure in ambitwister space. And the vertex operators are all about that. They're built out of Dolbeault cohomology classes that represent the perturbations of complex structures. And the other main selling point of the ambitwister string is that quantizing ambitwister strings gives rise, in the first case, to the CHY formulae, but also to various other formulae, depending on your choice of representation of ambitwister space. And so here, the key point is going to be that we can arrive at twistorial representations using the geometry of ambitwister space, and these give rise to new representations for field theory formulae. And in particular, they allow us to have some of the slickness of representations of supersymmetry that we found in the original twister string. So those formulae are going to be discussed by Yvonne, though, not by me. So I'm going to discuss the models. And so what I want to do first is to start off by reviewing the RNS model that David Skinner and I first came up with, and then review also how the original Witten twister string, Witten Berkowitz, and then Skinner twister strings fit into that. But also already in 4 dimensions, you do get a different perspective. You get a new model which gives rise to new formulae. And then I want to, so I'm going to spend most of the talk talking about the 6D representations and hopefully paving the way so that Yvonne can talk more slickly about the formulae that arise. But in terms, I'll focus on 5D and 4D because that's where you get models that are in some sense complete. So they're sort of somewhat heuristic models in 6 dimensions. And similarly in 10 and 11 dimensions, there's an element of the models, so to speak, exist partially, but they're not quite complete again. Okay, so to introduce the basic ambitwister string, we can start off with, as one might do in conventional string theory, with a word line action for a light ray. And so that's what I have up here. Yes, so I can draw on it, that's good. But it's not actually the light ray, because what I've got here is a Riemann surface, and instead of having d by d proper time, I've got d bar, which is the anti-holomorphic derivative with respect to the coordinate sigma on the Riemann surface. And in order to make that all make sense, you have to actually complexify the coordinates. So p and x, x is in complexified spacetime, which could be arbitrary dimension, and p is then the pullback of the cotangent vectors in that spacetime under x. So in this formula, in the standard way, E is a Lagrange multiplier that forces the fact that the momentum should be null, but it also has, it doubles up as a gauge field. And so if E goes to E plus d bar alpha, then what you discover is that that it's shooting you up and down the light ray. X goes is shot along the light ray and up by alpha p. So this action describes actually the quotient of the cotangent bundle by those gauge transformations on p squared equals 0, and this is the space of complexified light rays. And so this is a symplectic manifold, and it has a symplectic potential, which is what comes from p dot dx, that descends. So that's all very classical stuff. And where does the kind of Penrose transform twister idea come in? Well, it comes in because the space of light rays encodes space-time data in terms of deformed complex structure. And so how does that work? Well, because you've complexified, if you take a point x in space-time, that corresponds in ambitwister space to the whole light cone. And if you kind of projectivize the P, that's a compact complex submanifold, and such submanifolds are rigid. And you find that the moduli space of such manifolds is actually 4 dimensions. It is the original space-time. And the intersection of those submanifolds, x with x prime, gives rise to the fact that the points x and x prime are separated by a light ray. So, so the space-time in geometry is simply encoded in the complex structure of the ambitwister space. So, so the space-time metrics determined by it, and in some sense you can think of the one form p dot dx as actually determining the complex structure, because it determines the holomorphic one forms theta wedge d theta to the top power, determines the holomorphic volume forms, determines the complex structure. So, so this gives you a novel way of encoding space-time fields and data. And we'll see that in a moment, but just to go through sort of some standard sort of law, you can quantize this space in a normal way. You, as a string theorist might, you add in some sort of world sheet gravity in the form of a deformation of the complex structure of the Riemann surface itself. This is the E tilde in the formula there. And but you gauge fix, and you gauge fix E equals 0, you get ghost, BRST, and everything. And for the Q to be consistent, you get the standard anomalies or critical dimensions of string theory. So for that bosonic action, it's 26. And if you want to have some world sheet supersymmetry, then you go down to 10 with exactly the same as the standard closed string models that everyone imagine here is familiar with. And again, as everyone's familiar, again, you compute amplitudes by taking correlators of vertex operators. But of course, part of the point of this story is that our vertex operators are different from those of the standard string theorist. The payoff here is that with these models and with appropriate choices of worldsheet supersymmetry and matter, we obtain the full range of CHY formulae. But let me just say a bit more about the vertex operators, because they are what's tying in with this complex geometry picture that ambitwister space suggests. So as I say, field perturbations correspond to deformations of the complex structure of ambitwister space. And there's a standard law in complex geometry that such deformations are given by, they're given by cohomology classes. They can be given by Dolbeault cohomology classes. And in fact, what you discover is the symplectic potential theta, that's also the action, but it also encodes it's like a Hamiltonian for the deformation of the complex structure. And, but it's also the variation of the action, so which is another way that a string theorist might view at least the integrated vertex operator. So you work through the Penrose transform and you discover that the general vertex operator will have the structure I've given here, where that delta of k dot p, that's meant to be a delta bar, it's meant to be a Dolbeault 0,1 form, and it can be understood as d bar of, I could even write that in, oops, well I can, d bar of 1 over k dot p. So that's a Dolbeault 0,1 form that lives on ambitwister space and you have room for two worldsheet currents, W1 and W2. And these are usually built out of some worldsheet matter system like a current algebra, or if you have some worldsheet supersymmetry, you have a formula that's given down here at the bottom. And so one of the key results then is that if both W1 and W2 are in that form, then you get the CHY gravity formulae. So it's a type 2 gravity. Okay, so how did twistors fit in with this? Well, if you're working in 4 dimensions, then your light ray, you see you can solve the constraint p squared equals 0 by expressing p as a product of 2 spinors, lambda and lambda dot. And then a light ray determines both an alpha plane, which is twistor, Z, and a beta plane, which is a dual twistor, Y. So the alpha plane's along lambda alpha, and the dual twistor is lambda along lambda alpha dot. So these are uniquely defined by the light ray. And what you discover is that ambitwister space then, for the twistor and the dual twistor to intersect, you need to have a dot product between them vanishing. And then this is a description of ambitwister space. And so then what you see is that the original Berkovits model for the twistor string is in some sense just gauging out that constraint, y dot z equals 0. But you have choice of twists. So in the original twistor string, because the z and the w are in a sense independent, one can have degree d, and the other one has degree minus d minus 2, and that gives rise to the RSVW super Yang-Mills, and the, with some extra kind of worldsheet gravity, some Cassato-Skinner supergravity formulae. But you can also actually, if you wanted to regard them both on the same footing, the T and the T star, then they would have to have weight -1 on the Riemann sphere, in the sense of being a spinor on the Riemann sphere, and you'd write down an action like that. And you can write down then ambidextrous formulae, which is something that Yvonne and Arthur Lipstein and I did some years ago. So how does this work in 6 dimensions? Well, in 6 dimensions, spinors work a bit differently. If you, the spin group is SL4C, so it's the last example where the spinors have no purity and everything works very beautifully. You can express your 6 component indices in terms of skew pairs of spinor SL4 indices. And then the metric is thus given by the epsilon tensor on SL4. And what happens is that if your momentum vector k is null, then as a skew matrix, it has to have rank 2 instead of 4, because the Pfaffian has to vanish, k dot k vanishes. And so because it has rank 2, you can factorize it into a product of 2 spinors, and the freedom in doing so is SL2, but you have a choice of doing upstairs or downstairs. So you have the 2 chiral choices. So you have 2 little groups, SL2, I could have put an SL2 dot or SL2 tilde for the 2 sets of little groups. And so the picture now in 6 dimensions, analogous to the one in 4 dimensions, is that we could either work with a pair of twistors. So, so you have a twistor Z1 and Z2, but these are both on the same footing, and you actually have a SL2 freedom of rotating the 2 twistors around the light ray. And in fact, you could have done much the same thing, except with the opposite chirality twistors. So I'll call those prime twistors because they're no longer dual in 6 dimensions. And again, you'll have the other SL2 in describing the light ray. And so these twistors are actually pure spinors for the conformal group. So, so the conformal group in 6 dimensions is SO8. And you do get a purity condition there, which is just a dot product. So the nice triality story there is that the spin space for SO8 is also a representation of SO8. It happens to be a different one. And so we have each twistor is defined by a null element of C8. And you have the instance relation, which gives you the self-dual 3 planes that they correspond to now in 6 dimensions. And these will then intersect along a light ray if Z1.Z2 equals 0. So we get this sort of quite nice description then that ambitwister space is a pair of twistors whose inner products all vanish amongst themselves, divided by SL2. And this is neatly encapsulated in an action where you have a holomorphic map from a Riemann surface into the big twistor space, and you have a gauge field A, which imposes as a Lagrange multiplier for the constraints here, and but it also gauges the SL2, much as we had for the original action, the light ray action. But we have triality. So in fact, we have 2 other models which we could frame in the same way. So we have the primed, or actually I put them as dotted twistors, and that's an identical action, but it's the other chirality of twistor in 6 dimensions. And in fact, the space-time itself is a quadric in P7. It can be, and so we have a conformally invariant representation of space-time itself. And then a light ray is also a pair of points there, which happen to be null separated. And they have, but they are subject to an SL2 freedom because they're a choice of a pair of points on the light ray. So you have these sort of rather charming trial models. And this is closely related to a model that Tim and friends came up with some years ago for conformally invariant ambitwister strings. Okay, so how are the vertex operators going to work? We have, as I said, you have to think of a vertex operator as being associated to a sort of first cohomology class in ambitwister space. With I've got the L there, values in some line bundle. I don't want to go into details too much. I mean, it's just the scaling of P essentially. And that then, for the RNS case, encoded the K, had this delta function K dot P equals 0, imposing K dot P equals 0. That was, in some sense, the way in which the scattering equations come into the story. And but we need to rephrase that in terms of twistor variables. So instead of a P and an X, we're going to have lambdas and mu's. So the lambda P is a product of 2 lambdas. And so that's maybe the first thing you want to think about is how is it that k dot p can be encoded in terms of the lambdas. And so we have a lemma that says that if you have a pair of null vectors that are mutually orthogonal in 6 dimensions, k dot p equals 0, then the corresponding little group spinors are subject to a linear relation. So there exists non-trivial u's and v's such that u lambda is equal to v kappa. And this is the polarized scattering equations, which will play a big role in Yvonne's talk. And so we can, at the expense of having these extra u and v parameters, we can express this delta function in the standard vertex operator, and also the mu's. Somehow you can reuse this. There's an epsilon here. We can reuse the epsilon in the exponent to get the k dot x in terms of twistor variables. So these will underpin all the amplitude formulae, but we'll have to have some w's here for to write down some vertex operators. And if you just take a pair of current algebras for the w's, then you get biojoint scalar amplitudes in 6 dimensions, and these are conformally invariant. So you expect to get this conformally invariant formulation of biojoint scalars in 6 dimensions. But we also have an analog of worldsheet supersymmetry. And for that, we essentially introduce a pair of fermions, rho and rho tilde. And these are then gauged by analogs of Ricci-Schwinger fields, chi and chi tilde. And that they actually have, they don't actually have spin on the worldsheet in this model. Or at least they have 0.1 spin. But they're gauging constraints between the lambdas and the rhos. But they contribute to a vertex operator that you can write down. And the problem here is that you see, super Yang-Mills and supergravity are not chiral theories. They need both lambdas downstairs and dotted lambdas upstairs. But these live in different models. And so we haven't really been able to write down a coherent model in 6 dimensions. But in 5 dimensions, there is no chirality. You can identify upstairs and downstairs spinor indices with a skew form. And that really corresponded to the fact that you've taken a translation reduction along a vector, a non-degenerate vector in 6 dimensions to get down to 5. We can handle that in the model because this P, which is just the product of the 2 lambdas, gauges the translations. And so we can gauge that translation up and down the 6th direction. And then with that basic bosonic 5-dimensional ambitwister string, we can now throw in some worldsheet gravity in the current algebra to get Yang-Mills models. Or we can do 2 worldsheet supersymmetries type 2 to get a supergravity model. And what's nice, so this is sort of where David came into the picture, is that he computed all the anomalies for us, and he discovered that all the gauge anomalies vanished. So his first reaction was, oh, they're going to be anomalous, but they're not. And also, if you count the critical dimension, you find that it's exactly what you'd expect if you wanted it to have come from a model in 10 dimensions. So if you include an extra 5 dimensions, then it's critical. So although we've written down a model in 5 dimensions, it somehow really knows that it ought to have come from 10, in much the same way as when you do some strings models in 4 dimensions, you know that you had to have that Calabi-Yau in the fiber. Anyway, these issues don't really affect the 6-dimensional story if you were just interested in amplitude formulae. How much time do I have left, by the way? I'm slightly nervous I'm overrunning. Okay,
you have
well,
one more minute?
I have 1 more minute. Okay, well, I can fast forward, really.
Yeah.
You can do another reduction to 4 dimensions, and sort of one of the novelties here is that you can sort of twist the reduction. So you can pick out a current from the 5-dimensional theory, and say like a Higgs field, and this will give you massive models in 4 dimensions. So if I've only got 1 minute, maybe I'll just fast forward. I'll just say you can do this. Some of the details are on the slide, and I hope you'll write this up shortly. But it ties in nicely with the massive little groups and the way spinners work in massive spinners work in 4D and everything. And of course the anomalies work nicely as well, in the sense that it's expecting to have an extra 6D's worth of stuff at that point. If you want to go up to higher dimensions in this scheme, you have to have your twistors double every double in dimension every 2 dimensions, and so do the little groups. So if you want to go up to 11 dimensions, everything goes up by a factor of 8. So going up to 8 dimensions would be a factor of 2, 10 is another factor of 2, 11 is another factor of 2. But you can write down a model, and it looks pretty much like what we had before, and you have some constraints now which are much, much bigger and much more cumbersome to discuss. But you can still discuss amplitude formulae. Remarkably, this is very close to models that Igor Bandos had written down some years ago, so I was quite impressed by that. He doesn't have quite the same constraint structure because he wants to have some extra degrees of freedom for M-theory models. Okay, so just to finish off, the principle is that the linear geometric realizations of ambitwister space lead to different supersymmetric ambitwister string models. And they're all sort of trying to live in 10D. We had some vague hopes for 11. There are some incomplete stories. So there's a paper by Nathan, Max, and myself that's based on a wordline model that Nathan wrote down nearly 30 years ago. And somehow that actually sort of works out reasonably okay. And that the incompleteness there is really that I felt that the amplitude formulae we got were rather unpleasant, involving square roots in light cone gauge. We also had a go with Eduardo as well at a pure spinor 11D model, but then we got stuck with consistency conditions for vertex operators, but it's not necessarily dead. 6D is still obstructed for the reasons that I said, but the formulae sort of seem to live in all dimensions. And anyway, I still hope that there's some nice links to pure spinor strings. And maybe I put a remark at the end. Okay, the string field theory is field theory, but maybe there's something interesting there if we can figure out how to sort of phrase it in some analogy with the way that the stories that we've been hearing about earlier on in the week. And in fact, the links to conventional string theory still have a lot of mysterious aspects. It should be large alpha prime, but it really should be small alpha prime, and we're still up in the air about that. Okay, so I'll stop there and say thank you.
Thank you for the very nice talk, Lionel. So are there any questions or comments? Okay, please go ahead, Ezra.
Yeah, this is Ezra Getzler. Thanks for that talk. A really technical question, which is when you wrote down your vertex operator and you built it from a Dolberg cohomology class, is there a general formula relating the ghost number of the vertex operator with the degree of your cohomology class? That's my whole question.
Right, so the cohomology class has to be an H1 because it's a deformation of the complex structure. And the ghost numbers are coming from somewhere else. So the ghost numbers are coming from, really, when you go back to the world sheet supersymmetry, they tend to be associated with fixing the, they all have this Rita-Schwinger field, and you've got to fix the constraint there. And then you have ghosts and everything, and that's what gives rise to the various ghost numbers.
Okay, thanks.
Okay, Nathan, you have a question, right?
Actually, it's for both Lionel and Konkar, who I think is online. What's the relation between these two D equals 6 stories?
Well, Konkar is the person who wrote a nice article on that, so maybe I should let him answer. I mean, if he's too shy to answer, I can summarize it. Well, Sonkao, you go first if you're there. Well, okay, just to save time.
Maybe you can. Maybe you can.
Yourself, Sonkao.
So Sonkao's paper with John Schwartz, well, the perimeter group paper already proposed the existence of a Grassmannian associated with these formulae, and these various amplitude formulae all embed nicely in this Grassmannian. And basically, in this case, the Grassmannian happened to be the space of Lagrangian n-planes in 2n dimensions. And what Sonkao and John Schwartz showed was that that they're both, in some sense, gauge equivalent representations in the Grassmannian. So you know, they correspond to the same embedding of some 4n minus 6 dimensional sort of cycle into the Grassmannian.
So I think Sonkao now unmute the mic. Do you want to say?
I thought he computed some amplitudes for self-dual or self-dual two forms or something.
Well, there are formulae for sorry, not stacks, just single M5 branes in both. So we lack a model for that, in the sense that we don't have the correct worldsheet matter to provide it, but we can certainly write down the formula, and in fact our framework gave rise to different formulae from the ones, so the perimeter group, so this is when Sonkao, sorry, not perimeter, Caltech group, when Sonkao was in Caltech, had the first formulae for M5 branes. And so we have ones which are different formulae, and they're built out of the ingredients that we had. But yeah, so we can write down the formulae, but not models at this stage.
I think we can continue discussion with the informal discussion session. And let's thank Lionel again for the very nice talk. So let's move on to the second talk by Yvonne Geyer from Chulalongkorn University. So she's going to tell us about Twistorial ambitwister-strings, part 2, amplitude formulas. So could you start the share screen? Okay, please start.
Can you see me? Good.
Yeah, here. Okay.
Okay, great. Thank you so much for the invitation. And as you just heard, my talk is the second one in the series that is going to talk about what amplitude formulas come out of these Twistorial ambitwister string models. And maybe just to set the stage a bit, let me remind you of what Lionel just told you about with the ambitwister string and the CHY formula. The nice thing is that the formulas typically live in d dimensions, not the models. The models have a critical dimension, but the formulas are valid in any dimension. And the typical feature of these worldsheet representations of field theory amplitudes are some sort of localization constraints that you saw in the scattering equations or in the vertex operators, these k dot p's that Lionel had. And what they do encode is that p square, the same p that you just saw in the actions, vanishes everywhere on the sphere. Now, we do know, as also Lionel reminded you, that in 4D, the twister and ambitwister models actually look a bit different, and same in the vertex operators. What you find is a localization on something that is equivalent to these scattering equation formulas, but they're actually refined by MHV degree, and you can see this here in this spinorial format that I've put at the bottom of the slides. For our purposes, what is going to be most interesting about them is that they have manifest supersymmetry. And so, as you saw from Lionel's talk, there is a natural question whether whether you can extend these formulas to something that lives in higher dimensions. And I'm going to talk specifically about 6D today, with reductions to 4D massive and 5D being relatively straightforward. Yeah, so that is what is going to be my focus on today. And in particular, we'll see what form these localization conditions take. And I'll give you a brief motivation how they come about from the ambitwister string models that Lionel told you about. Before diving into that, because Lionel mentioned it and because we'll use it later, I just want to actually briefly review for you what form the CHY amplitudes take. So this is the form of the scattering amplitudes for massless quantum field theories that naturally comes out of these RNS-like ambitwister string models. Now, the first thing that I want for you to notice that this is all talking about massless quantum field theories. So I'm going to be in d dimensions here, but always massless. And as a good worldsheet formula should, we're integrating over the moduli space m0n of marked Riemann spheres. But this is a worldsheet model for a field theory, or a worldsheet expression for a field theory amplitudes. And so this expression is actually fully localized on a set of constraints that I've called EI here for the scattering equations. And since they play an important role, I just want to briefly also tell you how they are constructed. So the nicest way to tie into the models to construct them is to first define a one form P that is just Ki over sigma minus sigma I. You can see what this does. It associates the momentum Ki to the puncture sigma I. And then these constraints just tell you that the residue of P square vanishes on all marked points, which in turn means that P square will vanish everywhere on the sphere. Now, if you can just calculate this, and this gives you the familiar K dot P's that you saw in the vertex operators just before. Yeah, so let me just stress this fully localizes the worldsheet integrals that we see here. So the prime in the product here indicates that we're modding out by the Möbius invariance. And so there are n-3 of these equations, which are exactly the correct number of constraints to fully localize the integral over the moduli space. Now, the last ingredient here is the worldsheet integrand. And while the rest is universal for all massless field theories, this integrand is really what tells you what theory we're talking about. And for all theories that we know, it splits into two parts that are called half integrands sometimes. And both of them depend on the typical data of the theory. So the polarization that you put in, the color structure, these things. Okay, so what these formulas do very well for us is they provide one of the most compact amplitude representations that we have in d dimensions. And as Lionel already indicated, they hold for various theories, and they have the big advantage of having, at least for type 2 supergravity, a critical worldsheet model, the RNS or the pure spinor one, which allows you access to loop amplitude calculations. The one thing that they really don't do well is giving easy access to endpoint amplitudes with manifest supersymmetry. And on the other hand, the 4D Twistorial models, or Twistorial's realizations of ambitwister space, do exactly that. They don't hold for any dimensions, but they give you nice supersymmetric, manifestly supersymmetric amplitudes. So really what we're going to try to do today is see whether we can find formulas beyond d equals 4 here. Now, Lionel already gave you a brief review of spinor helicity in 60, but just to review and to set the notation a bit, I'm going to be looking at vectors k with, as Lionel had, I'm going to have my spin indices SL4C denoted by A and B. And if k is null, we actually know that KAB has rank 2 because it is also antisymmetric. And so k can be decomposed into two spinors, k, what they call here kappa, depending on whether you have the spinor indices up or down, with an additional little group index. And KAB can be written in this 4D inspired notation for the contractions between these two kappas. Now, for the amplitude formulas, we'll also need, especially since we're mostly interested, for the first part at least, in super Young-Mills and supergravity, how to encode polarization data. And that is just a field strength FAB up to F, up to the trace being 0. But for momentum eigenstates, this simplifies drastically with the epsilons that already, the just spinor epsilons that already appeared in Lionel's talk. And these will play an important role in just a second. So with this background, let's just take another look at the scattering equations from before. So let me remind you, these just have the form k dot p equals 0. And what they really encode for us is that p square vanishes everywhere on the sphere. Now, what we're really after is some spinorial resolution for this, similar to the twistor string or the RSV or RSVW formulas that come out of the twistor string models. Now, since P is null, we know we can at least try to decompose P into this contraction of lambdas just by the same argument as before. And if we do so, then the scattering equations, the k dot p, are just equal to the statement that the determinant of the kappas and the lambdas have to be 0. As Lionel said, there's an easy lemma to show that this is equivalent to there being a little group rotation, essentially, that translates between these lambdas that define the p and the kappas. Here, we're just saying that the UVs are some variables that we can define such that the equation above holds. And there's in fact some freedom. So we can have a further freedom to normalize one of these degrees of freedom, for example, in V, by saying, for example, that V epsilon is 1. Now, the real need of this, up to this point, we haven't really said much, is finding an expression for lambda that is correct. And inspired from 4D, a typical ansatz that you could make is to put lambda equal to the sum over all particles with U epsilon over sigma minus sigma I, where the epsilons are exactly the polarization data, the little group polarization data contracted into the kappas that we had before. Now, to see that this is actually correct, because at this point it is just an ansatz, note that so it automatically satisfies the scattering equations by construction. We constructed these polarized scattering equations so that they will always imply the scattering equations, and that's p squared 0. What you really have to check here is that using these polarized scattering equations, the p that we have written down above actually reduces to the p that is in the top right corner here. That's actually a very easy calculation. It fits either on the back of an envelope or even on my slide here. So you just calculate the residue at a marked point, sigma I. Well, first of all, we note that there's actually no double poles because U contracted into itself vanishes. And when you calculate the residue, you just end up with a very simple expression that on the scattering equations, these polarized scattering equations here, directly reproduces for UK. So this ansatz is indeed correct and reproduces for you the P that we had above. So what we've written here, the polarized scattering equations with the ansatz actually give you a correct spinorial resolution of the scattering equations. Now, it's not trivial from the form of them, but you can show that there's actually a unique solution for these U and B's for a given solution sigma of the scattering equations. That is very nice because in some sense we do not want to introduce additional complications here. And so it's very nice to see that there is in fact a unique solution, despite the fact that naively at least these equations don't look linear. And let me just point out that there is a very natural measure. We'll look at that a bit later in more detail, but you can already, if you're familiar with these with these worldsheet formulas, you can probably guess what it is. You just integrate over every variable inside, divide out by the correct symmetries, and localize on these polarized scattering equations together with the normalization condition for the V that we chose. Okay, before diving into the amplitude formulas that we could construct like this, let me also briefly just talk about supersymmetry in 6D, since our main motivation was to actually find nice, manifestly supersymmetric formulas. Now, in general, we'll want to look at N tilde supersymmetry with SPN cross SPN tilde R symmetry group. But for on-shell supersymmetry, we have to choose supermomenta that are just a subset of these supersymmetry generators. And in fact, we'll have to roughly reduce twice. Now, on momentum eigenstates, one of these reductions you essentially get for free. as I've shown here on the slide. The second reduction is more tricky, and you have to give up either manifest little group symmetry or manifest R symmetry. So Nathan, maybe that goes towards your question from before. The manifest little group, keeping little group symmetry manifest is what was done in the Caltech perimeter papers. What we're doing here is making R symmetry manifest, because the polarized scattering equations that we were writing, if you remember, already with the choice of the epsilons here, already sacrifice manifest little group symmetries. For us, it's a more advantageous choice to keep R symmetry manifest, but for these specific ones, there is actually a fermionic Fourier transform that just interpolates between the two. Now, that said, what we're going to do is we're going to choose our supermomenta Qi to be defined by the following equation, where my psi here and my epsilons are just some basis for the little group of the given particles. So you can see here explicitly that I've sacrificed manifest little group invariance, and the Q's will be my supermomenta. Just to give you a bit of a feeling for what this will look like, you can see below I've spelled out the supermultiplet for n equals 1, 1 super Yang-Mills there with its corresponding supersymmetry transform. And what this will look like in this representation for a momentum eigenstate is as follows. So we'll have the field strength being leading order in the supermomenta, and then also coming in at both at the lowest order and at the middle orders. And for example, I've given here one of the fermions that you can see will come in at order Q tilde, where Q tilde is the corresponding one for the n tilde supersymmetry, the supermomentum for the n tilde supersymmetry. Okay, so with this in place, let's look next at what amplitudes formulas you can actually try to construct out of these. So we've seen a lot of ingredients already, and the rest will fill in afterwards. So firstly, we've already talked briefly about the polarized measure. So what we know is that it should localize on these polarized scattering equations that I've spelled out for you, just to remind you. And I've also put in the normalization constraints. The prefactor here is just what I said before, basically integrate over everything in sight. But notice the symmetry that we're modding out by. So there's the usual SL2C that I've denoted here with the subscript sigma, that is the typical moduli space of the Riemann sphere symmetry. There's an additional SL2 that I've denoted here by U, that is a global rotation under use. And we'll see later that this ties in nicely with the ambitwister models that we've seen. It's easy to see that the scattering equations respect this global SL2 rotation if you look at the form of the UU contractions in the U lambda term. Now, let me just point out that this again fully localizes it, the integral, and it's easy to count. So you have 5n delta functions that you see here, 5n variables, but 6 degrees of freedom coming from the symmetries. And so you'll be left with exactly 6 delta functions that correspond directly to momentum conservation. And you can easily check that the polarized scattering equations actually encode momentum conservation for you. Okay, so the integrand, I haven't yet said really anything about it. I kept it the same form as before for the CHY-like formulas, and the reason for that is simple. You can actually show that the polarized scattering equation measure that I've just wrote is exactly equal to the CHY measure. So we certainly know that if we choose the integrand to be the CHY type integrand, we'll actually end up with correct amplitudes formulae, although in that case, without supersymmetry factors, they obviously wouldn't be manifestly supersymmetry invariant. The only new thing that I want to tell you here is that same to the CHY formulas, the integrands always split into 2 half integrands. And for Yang-Mills in gravity, these half integrands respect the double copy. So we can construct the Yang-Mills integrand by choosing one color part that I've called here the Park-Taylor factor. This is the typical Park-Taylor factor that you're very familiar with. And the other half integrand is what I've just called kinematics in reference to the color kinematics duality. And gravity, you get 2 kinematic components here. Really, this kinematics is encoding your spin 1 degree of freedom, so if you want to think about it that way. Now, last but not least is the supersymmetry factor. And it turns out that for the above form of the supersymmetry generators that I've written down, the correct choice of supersymmetry factors of the form e to the f plus f tilde, where f spelled out f here and f tilde is defined the same for just with q tilde. You can see some similarity here, at least in the first term, the ui uj over sigma ij term that also appears in the polarized scattering equations below. And the second term is just something that is local to each vertex. Now, the reason that you should write it down like this is very simple. You can check that supersymmetry invariance holds. So if the whole rest of the formula does not depend on the supermomental, you can simply check that on the support of the polarized scattering equations, this form guarantees that the whole amplitude is actually supersymmetrically invariant. Okay, so the only ingredient at this point that we have not talked about are the integrands. And these will be natural generalizations of the 4D integrands, but I will not at this point derive them. I just want to actually just show you what they look like. So for spin 1, this is a reduced determinant that is actually very reminiscent of the reduced determinants that appear in 4D, for example, in David Skinner's first model. For the brane theories, the building blocks in this case were first written down or first identified in a slightly different form by the then Caltech group with Heidemann, Schwarz, and Wen. And the important components are this Pfaffian prime of a matrix A that also features in the CHY. And you can see that this is the only component that is not typically, that doesn't look as though it naturally fits in the spinorial framework. I should also say we could have chosen a spin 1 representation of the half integrand that is the same as in the CHY formulas, but that just doesn't sit naturally in the spinorial formulas. Now, the other component is a Pfaffian of U with U as defined here. And there'll actually be two types of combinations that we can make out of this, as we'll see in just a second. Last but not least, the Park-Taylor factor that we're all familiar with. Now, with these building blocks, there's actually 4 types of half integrants that we can construct. Now, the Park-Taylor and the reduced determinant are natural building blocks by themselves, where I've put it here, the reduced determinant with the correct supersymmetry that is typically associated to a spin 1 for maximal supersymmetry. And out of the Pfaffian prime A and the Pfaffian U, both of them don't carry enough weight in the sigmas to be half integrants of their own, but we can construct either a reduced determinant of A or this ratio, the Pfaffian prime A over the Pfaffian U, that is very typical for brane theories. So just to highlight for you where our favorite theories sit in here, in this column here that I've marked in red are the sort of super Young-Mills and supergravity, and you'll see that also d5 that we'll get there in a second sits here. And in the row that I've highlighted in orange here, we have our favorite brane theories, so d5 and m5, where, let me just reiterate, so these were originally written down by Heidemann, Schwarz, and Wen, and I've adapted that formalism here to fit within our polarized scattering equations. Okay, since I have a little bit of time left, let me actually just tell you in a little bit more detail how these formulas fit into the worldsheet models that Lionel talked about in his last talk. Now, just to remind you, I gave you here the action of the ambitwister string, just the super ambitwister string in this case, but without any additional worldsheet matter. And let me remind you also of the form of the vertex operators. So first of all, this maps us into ambitwister space. And as Lionel told you, a crucial factor for that is these localization on this u lambda minus v kappa that is already very reminiscent of the polarized scattering equations that we've just seen. On the right, I've also included the full supersymmetric factor in the exponential. And I just want to point out that there's this local term, 1/2 psi v qi square, that we also saw that is very typical in the supersymmetry factors. In fact, of course, these vertex operators are constructed to match these. Now, as Lionel briefly alluded to, what we are after is just a correlator, and these correlators are in fact very easy to calculate, or relatively easy to calculate, because after gauge fixing, all CFTs become free and linear. So the calculations are actually very straightforward and certainly not as involved as the corresponding calculations in string theory. Now with the vertex operator as before, so I've dropped a few terms here just to make it more readable. You can see that it's actually very easy after gauge fixing to integrate out the lambda mu system. And what it does for you is it just localizes the lambdas onto their classical equations of motion with sources provided by the u mu epsilon term that sits in the exponential. Now it's easy to solve this, and plugging it back in, you can see that we recover immediately the polarized scattering equations. Now we can basically repeat the same game for the eta system, where eta was the, let me just remind you, the fermionic component of the super ambitwisters. And if you do so, what you end up with is a very similar looking equation of motion, again sourced by the exponential, and plugging it back in, you find the contact term, if you want, in the supersymmetry exponential factor, with the local terms, the terms that are local to each vertex just staying the same as they are. Now, plugging this back in, you can easily see that I've motivated where most of the ingredients in the formulas come from, except for the integrands. And as Lionel discussed in more detail, the reason for this is that, at least in 60, there's really no good model at this point for the integrands. With the reason being that ambidextrous integrands with one supersymmetry, as we would like for super young mills, just don't, you would have to resolve the constraints that are actually prohibitively difficult in these models at this point. Now, since both of these are now, so you've seen now two ways of getting, well, briefly at least, two ways of getting to these formulas. One taking the route from a CHY type formula and trying to resolve this, making sure that you ended up with a supersymmetric formula and a spinorial resolution of the scattering equations. And that is certainly a good indication that you're on the correct track, and guarantees for you by supersymmetric invariance and the correctness of the top amplitudes, that the amplitudes actually have a lot of the correct properties that you want. And the other one was a motivation from these worldsheet models, but as you heard, at least in 6 dimensions, there's certainly issues associated with that. So I just want to tell you very, very briefly how you actually go about proving that these give valid representation of field theory amplitudes. And the idea is something that is very typical in the amplitudes community. And let me just briefly review it for you. It's what goes under the name of BCFW recursion after the authors Pratap Kashyap and Whitten. And what we do is just we take two momenta, in its simplest form at least, and deform them by a complex variable z times a vector that we choose. And then for gauge theories and gravity, you'll have to make good choices for this vector. But even before that, you can see that there's immediately some constraints on this, because you want this deformation preserve all on-shell conditions. So that certainly tells you that q square and q dot k1 and kn has to vanish. Now with this deformation, you know that the original amplitude is just the one that is undeformed. And in fact, it is still a valid formula, amplitude formula away from there, because you chose your deformation such that it preserves all on-shellness conditions. But that lets you apply a neat trick, which is just a Cauchy residue theorem that wraps the contour around, and instead of the residue at z equals 0, you pick up whatever other pole the amplitude in this case has. But by, for example, the optical theorem, we actually know what most of these poles are. Basically, all of them are just factorization channels of the amplitude, where some internal propagator, KL, the shifted version of that, goes on shell. Now, potentially there might be terms from infinity, but it turns out that at least for super Young-Mills and supergravity, or Young-Mills and gravity in general, these terms are absent. And so BCFW and follow-up work showed that for Young-Mills and gravity and supersymmetric versions thereof, amplitudes satisfy a recursion relation that I've depicted here schematically, where you sum over contributions of lower point subamplitudes connected by a propagator 1 over KL square. Note that KL square here is finite. It's a shifted K hat L that goes on shell. So what we did to prove our worksheet formulas is prove that our formulas actually satisfy this recursion. It's a bit technical, but the idea for all of these scattering equation-based formulas is always the same. And it's actually surprisingly ingenious, because the integrand, the worldsheet integrand, if you remember the form, for example, of the Park-Taylor factors, only has poles at the boundaries of the moduli space. And what the scattering equations, or in our case, the polarized scattering equations, do for you is they map these boundary devices of the moduli space to factorization channels of the amplitude. And you can use this correspondence to also identify the residues of this. And once you have done this, it is relatively straightforward to see that our worldsheet formula actually satisfies the BCFW recursion. Don't know how.
Could you wrap up the talk?
Yeah.
Could you wrap up the talk? Yeah. Okay, that's right. Okay.
I was about to say this is my point for wrapping up, but since we're sort of running late on time, let me just briefly say my summary is short anyway. But hopefully this convinced you that there are nice twistorial formulas in 6D, and you can reduce them in fact to 4D and 5D and find very similar formulas. And what would be really interesting, as Lionel already alluded to, is to see actually critical worldsheet models for these in 5D, critical up to the fact that you have compactified 5 dimensions. And while it would be nice to make some progress in 6D, there's certainly issues associated with that make it less straightforward. And let me just mention that there's also been some very recent work on making connections with some loop amplitudes using a dimensional reduction procedure. So it would certainly be interesting to see that played out more fully. Thank you so much.
Thank you for the beautiful talk. So we are running out of time, but are there any quick questions? So are there somebody raising hands? Okay, so I think we can move on to the next talk, and then we can discuss during the coffee break or after the informal discussion session. So thanks again for the very nice talk, Yvonne. Okay, so the next speaker is Subhroneel Chakrabarti from the Institute of Mathematical Sciences, Chennai and HBNI-Mumbai. So she's going to tell us about scattering of massive states in pure spinor formalism. Please start.
Okay, let me start by thanking the organizers for giving me this opportunity and also organizing this conference over online. So this talk is based on these 3 works, which was done with my collaborators Sitender and Mrityunjay. So pure spinor formulation is a manifestly superpoincaré covariant worldsheet theory of superstrings. So it contains the good part of RNS, which is Poincaré covariant, and it contains the good part of Green-Schwarz, which is manifestly space-time supersymmetric, and kind of combines them together. And this was introduced 2 decades ago by Nathan Berkowitz. And there are a lot of good things about pure spinor formulation, but just for this talk, let me specify one particular aspect. It has been tremendously successful in computing scattering of massless string states. And especially at loop levels, it surpasses the well-known RNS formalism approach. And there are many people who have worked in it. It's a partial list. But despite this huge success for the massless external states, one must say that the massive states remain comparatively unexplored. So there has been some works on the massive states. Let me point out 2 extremely important and seminal work. One has been the unintegrated vertex construction for the first massive states by Berkowitz and Chandia. And this was a very, very long time ago. And rather recently, there has been a DDF-like construction given by Renann. So the point is that we have some amount of information about the massive states in pure spinor, but it's not as much as is known as compared to the massless states. So there has been some general arguments which establishes the equivalence of the spectrum between the PS, pure spinor, and the RNS and Green-Schwarz formalism. And of course, you can compute amplitudes, any endpoint amplitudes at tree level, and there are several amplitudes which has been computed at 1 loop, 2 loop, and even 1 for 3 loop. And those corresponding amplitudes, if you compare them with the corresponding RNS formalism results, you can actually explicitly establish the equivalence between pure spinor and RNS formulation. And the question that we would like to address in this particular talk is that what about such explicit equivalence for amplitudes computed in involving external massive states? So this is just a one-slide summary of pure spinor formalism. It's an injustice, but for sake of time, we have to go through with it. So let me tell you that for this particular talk, I will be focusing on open superstrings, but hopefully towards the end of the talk, it will become clear that everything that I've said for the open superstrings could have equally been said about the closed superstrings, heterotic or type 2. So it's just for sake of specificity that we are focusing on the open superstring. So the wall sheet action is given by these variables. So this theta is the supercoordinate in the space-time. The p is the conjugate momenta to it. This lambda is a Majorana wild spinor, which acts as a ghost in this wall sheet action. And the W alpha is a conjugate to that. And this lambda basically satisfies this mathematical identity, lambda comma m lambda equals to 0, which is known as pure spinor constraints, and hence the name for the formalism. And the point is that this formalism, this wall sheet action written as it is, doesn't look very much space-time supersymmetric. But if you create the variables del xm for pi m and p alpha to d alpha, which are some combinations which we need not worry about in this talk. And these are essentially, if you're familiar with Green-Schwarz formulation, these are the Green-Schwarz variables. Then this Green-Schwarz, written this in terms of this Green-Schwarz variables, this is actually manifestly space-time supersymmetric. So because of this pure spinor constraints, you can see that this wall sheet formulation actually enjoys a gauge invariance of this form. And to sort of take into account this gauge invariance, it's a good thing to work with this gauge invariant combination, which are NMN and J's. This NMN has the interpretation of the Lorentz ghost current, and this J has the interpretation of the usual ghost number current. And one trade-off that you have for working with this pi d fields, which keeps the space-time manifestly, space-time supersymmetry manifest, is that they no longer satisfy free field OPE. So the ordering of any composite operators in this wall sheet formulation involving these objects actually matters. And for our work, we adopt this particular ordering convention. But of course, whatever physical result that you ultimately compute is independent of this choice of convention. And one particularly striking thing about pure spinor formulation is this beautifully simple form of the BRST charge. And the nilpotency of this follows immediately from the OPE of D and the pure spinor constraint. So a vertex operator in pure spinor, or rather more specifically the unintegrated vertex operator for the pure spinor, takes this schematic form. It can be written as a sum over some operator OI and some superfield SI. These OIs are basically some object created out of these matter fields pi d del theta and these ghost objects nj lambda. And the guiding principle is that for nth massive states, the unintegrated vertex must have conformal weight n and ghost number 1. So this OI is decided appropriately. If you're a little surprised about this conformal weight n, it's just because of this vertex operator is being considered without the plane wave factor. If you incorporate the plane wave factor, then of course it has the correct conformal weight or the more familiar conformal weight of 1. And this SI is a superfield which is essentially needed to appropriately construct all the Lorentz spinor and the Lorentz spacetime indices that comes from this OI operator. So just to summarize that this pi d del theta n j, all of these have conformal weight 1 and they have 0 ghost number. Lambda is the only one which has a ghost number, but it has conformal weight 0. Now, how do you construct this unintegrated vertex in pure spinor? So one way to construct this vertex is to sort of solve the BRST condition, QV equals to 0, which you can simplify it like this, and you can rewrite it in terms of this O tilde and S tilde equals to 0. This O tilde is essentially some operators that you get out by acting the BRC charge on it. And this SI tildes are sometimes the superfield SIs, and sometimes these will contain the covariant derivative of the superfields SI that appears in the vertex. And essentially, you have to solve for this equation. So ideally, you would like to set SI tilde equal to 0 and thinking of all the Y tildes as linearly independent. But we will see that due to the pure spinor constraint, this is not true. So we'll focus on the first massive states in open superstrings. And this is well known that it contains the spin 2 massive supermultiplet. It contains two bosonic fields, BMNP and GMN. BMNP is a 3-form field which satisfies these constraints. And GMN is a traceless symmetric field which satisfies these constraints. And Chi-M alpha is a spin 3/2 tensor spinor field. So Berkowitz and Chandia, they constructed the unintegrated vertex for this particular supermultiplet. And the basic point is that to construct it, all the unknown superfields SI tildes that I showed here, they all must be expressed in terms of a physical on-shell superfield BMNP and its supercovariant derivative. So let's quickly review the Berkowitz-Chandia construction. So essentially what you do is that you write down all operators at weight 1 and ghost number 1. For example, del lambda alpha is a weight 1 and conformal weight 1 and ghost number 1 operator. And because there is an alpha index hanging around, you multiply it with a suitable unknown superfield capital A alpha, and similarly for other objects. So then you remember that every unintegrated vertex operator enjoys a BRST gauge symmetry of this form. And with some field redefinition and this gauge fixing of this gauge symmetry, you can make these choices, which were made also by Berkowitz and Chandia. And I remember I told you that not all of these operators are independent. And it's because of pure spinor constraint, you can show that this particular identity is true. And the way to deal with this identity is to promote this at the appropriate conformal weight for QV equation, and then contract them with an arbitrary Lagrange multiplier superfield KSMNP. And then essentially you get some equation which is identically 0. So this is not a dynamical equation for K. This is something that follows directly from this condition, and this is something which follows from pure spinor constraint. So this is something which is identically 0. But if you add this left-hand side to the QV, then essentially what you can do is that you would have made all the operators linearly independent, and the resulting equations, you can set all the superfield part to be equal to 0. So if you do that, so QV plus Lagrange multiplier term equals to 0, you get this formidable set of superfield equations, and they look very scary, but it was remarkably solved by Berkowitz and Chandia. And all of these superfields were expressed in terms of a single on-shell superfield BMNP and its supercovariant derivative. And they did a rest frame analysis to show that this on-shell superfield indeed contains the correct degrees of freedom that you would expect for the first massive states. Now you may say that what more do we want? The construction exists for the unintegrated vertex operator. So the first thing is that vertex operators are used to compute scattering amplitudes. And in pure spinor, if you want to use a vertex operator to compute scattering amplitudes, you need its full covariant theta expansion. The Berkowitz-Chandia construction, however, only allows a perform a theta expansion in rest frame. So we need to do better than that. We need to do a covariant theta expansion. So there is a room for improvement here. But also we need a general prescription to repeat this feat for integrated vertex operator for the first massive states, as well as higher massive states unintegrated and integrated operators. So the goals are as follows. We want to give a systematic procedure to construct massive vertices in pure spinor. We also want to construct a full covariant theta expansion of this vertex. And essentially, once we have done that, we will be in a position to compute scattering of massive states fully covariantly. And we can compare with RNS and extend the explicit equivalence to include massive states. So a systematic procedure to construct massive unintegrated vertex is as follows. So first step is what I have described before and what Berkowitz and Chandia also did. You write down the most general conformal weight n and ghost number 1 operator for the nth massive state, and you contract with some arbitrary superfield. So for example, for n equals to 1, you write down the same answers that Berkowitz and Chandia wrote down, and you proceed from there. Now, step 2 is a point of departure from the usual Berkovits-Chandia construction, is that instead of working with a single on-shell superfield, we introduce a superfield for each physical field that is there in the supermultiplet. So if I have NB number of bosonic superfield, I introduce capital BI for each of a capital BI superfield for each of them. And if I have NF number of fermionic superfields, I introduce capital FI for each of those fermionic superfields. And the basic idea is that any algebraic conditions that are satisfied by the small BIs and small FIs, we promote them to the superfield level as well. So let us look at an example for the unintegrated first massive state. So we have a small BMNP, so we define a capital BMNP whose theta equal to 0 component is this. Similarly, capital G and capital Chi. And remember, we had these conditions for the physical fields in the multiplet that Km Chi M alpha is 0 and so on and so forth. We promote them to the full superfield equation, and we take them as the definition of this capital B, capital G, and capital Chi. The goal is that we right now want to construct a vertex which will be expressed as a linear combination of these superfields, but not their covariant superderivatives. That part is important, and I will come to it later as well. So step 3 is essentially derive all constraints between operators OI at some conformal weight n and host number 2. And essentially you handle them by introducing some Lagrange multiplier, or if you can eliminate them to have one operator in favor of the others, you should do that. And you should incorporate them in the BRST condition. So for example, this was the identity that was incorporated by Berkovits and Chandia as well for their construction. You do the same thing here as well. So for step 4, we use representation theory of the little group SO9 to write down answers for each unknown superfields as a linear combination of the physical superfields BI-FI. So let me spend some time on this for this particular example. So remember that the unintegrated vertex had one unknown superfield as an ansatz, which is F alpha Mn, and this is antisymmetric in Mn because Nmn is antisymmetric in Mn. So the first thing that we do is that we write down that this F alpha Mn in rest frame, it can have two sorts of component. So this A and small b are the spatial indices. So it can either be of the form alpha 0a or it can be of alpha ab, both spatial. So for example, let's look at this case. So this has a representation 16 times 9, and you would expect from group theory that it will have a representation in terms of 16 and 128. And we recognize that 16 is an unphysical rep for this particular massive supermultiplet, whereas there is indeed a spin 3 field which is of the representation 128. Similarly, for F alpha AB, you can do an analysis and you can do 16 times 36 to get that there is another 128 lurking here, but there are two other unphysical rep. And what we conclude from here is that this F alpha Mn should be written as two independent tensor structures linear in the physical superfield Chi M alpha, which corresponds to this representation 128. And at this point, you can essentially just by investigation figure out what those tensor structures are, and you multiply them by some arbitrary coefficients, and fixing F alpha Mn or for this on-shell vertex now boils down to fixing this coefficient small a and small b. Now for the step 5, what you do is that you do write down similar answers for the supercovariant derivative of the physical superfields using representation theory. So let us look into the example directly. So if you have the superfield GMN, you take d alpha of it. I use the representation theory of 16 times 44. I see that it's 128 plus 576. So that it must have a single tensor structure in terms of a field Chi n. And with some arbitrary coefficient, I write this thing down. Similar expression for d alpha B, M, and P, and d alpha capital Chi. And the point is that we need this relationship for two reasons. One is that, as I said, that we don't want to have covariant derivatives of superfields appear in our vertex anymore. And the second thing is that we will see that this chain of relations are the ones which will actually allow us to do completely covariant theta expansion of the vertex. So final step is that you essentially write down these answers and try to solve QV equal to 0 for each independent structure, because now the whole superfield set of equations has boiled down to solving a set of algebraic equations fixing those unknown coefficients. And you also have to make sure that the answers are consistent with the definition of the physical superfields, and also of course all the answers should be mutually consistent. And this completes the construction for unintegrated vertex at nth mass level. Now you may say that you gave some prescription, how do you know that this works? Of course, I have not derived it for you. So the way we know it works is that we can give you some evidence. First and foremost, it reproduces the Berkovits-Chandia vertex for n equals to 1, as well as the rest frame analysis. And this is an important consistency check. Next, it gives a complete covariant theta expansion of the Berkovits-Chandia vertex. And this is completely consistent with the Berkovits-Chandia vertex. And it's a new result. And it can be readily extended to the integrated vertex, which was constructed for the first time for the first massive states. I will not go into details of this because this is what Sitender will talk about right after this talk. So I strongly encourage you to listen to that. And finally, for the first massive states, this vertex, we will see that it gives the same result as the corresponding RNS amplitude computed using the corresponding RNS formalism. So let me just briefly describe that how this theta expansion actually works. So remember, for the first massive state, I told you that this chain of relations of covariant derivatives of the physical superfields are the ones that will actually help us in determining the theta expansion covariantly up to all orders. So let me describe how it works. So these coefficients are fixed after working with QV equals to 0. So I know I have rushed a bit on the construction of the covariant construction of the vertex, but you will get to hear it in a much more details in the next talk. So even if you have not followed the complete construction, know this, that these relations are completely consistent with what Berkovits-Chandia wrote down as their vertex. And also they wrote down corresponding some relations in the rest frame only, and these indeed reduce to their rest frame results. So one good thing about these relations and why they help us is this fact that when you take two covariant derivatives, and you multiply them with Km and the gamma alpha beta, they are actually proportional to the K square. So this actually allows you to invert these relationships in some sense. So if I act on this, for example, with another covariant derivative, I can do this manipulation to convert this into just a proportional to capital Chi, whereas on the right-hand side, I will have covariant derivative of G and covariant derivative of B, which I can use this relation to once again rewrite in terms of Chi. So you can understand that all these coefficients cannot be completely arbitrary. They have to be fixed from this self-consistency. And the rest of them are fixed by demanding that these superfields actually solve the QV equal to 0. So how do they help us in getting the covariant theta expansion? So let me write this set of equations a bit more simply and schematically in this way. So capital D is an operator which is defined like this. You can think of capital D acting on a particular superfield. L number of times picks up the theta to the power L component of that superfield. So that's how capital D operator works. So this basically gives us a recursion relation. So for example, look at the first one. We know that by definition, the 0th order theta expansion of capital G and capital B by definition is small g and small b. So the first theta expansion of capital Chi is given in terms of the 0th theta expansion of capital G and capital B, which acts as a seed to this recursion relation, and we know what they are. And essentially, when we have this, we can basically now, once we have the first theta expansion of first theta term of the capital Chi, we can go into this relation and fix up the second theta expansion or the first theta expansion of capital B. And we can do this recursion relation again and again. And because theta is a fermionic variable or a Grassmann odd variable, it terminates at some point. In fact, it terminates at theta to the power 16. And essentially this way you can figure out the whole theta expansion of the vertex. Now, of course, this theta expansion gets more tedious as you go into higher and higher order in theta. And but in principle, this is extremely simple to do. So one way to do this is to essentially encode this or automate this whole process in Mathematica. We used a package called Gamma, which was a lifesaver, and you can essentially get the full theta expansion. So for example, this is the theta expansion of the capital Chi field up to order theta cube. You could have proceeded more than that, but you can see that the expression gets bigger and bigger. And similarly, there are expressions for capital B and capital G's theta expansion, which you can find in our paper. So once we have the full covariant theta expansion, the meaningful thing to do right now is to essentially compute some amplitudes and compare them with the corresponding RNS thing. So let me quickly summarize or remind you that what was the tree-level amplitude prescription in pure spinor. So essentially, if you have an endpoint amplitude, tree level, three of them you can use the SL2R to fix. So you can use the unintegrated vertex for that. And the rest of them, you can have to use the integrated vertex and you have to integrate over them. So for this talk, we will focus only on the 3-point vertex. So we don't need to worry about the integrated part for now. And this actually factorizes into two parts. There is this plane wave part, and then there is a V1, V2, V3 part in the pure spinor superspace, which is what we have described here. The plane wave part is, of course, it's extremely familiar to us from our bosonic string theory. So this is something that we already know. We don't need to worry about that. And the pure spinor superspace normalization is defined or schematically often written as lambda cube theta 5. I will explain what this means. So we basically need to only evaluate this V1, V2, V3. And what it basically means is that you have to keep only those terms which have contained 3 powers of lambda and 5 powers of theta. The rest of them, by this normalization, actually trivially vanishes. Now each vertex, an integrated vertex, is already at ghost number 1. So obviously this is automatically at lambda cube. So we don't need to worry about the lambda cube part. But you have seen that for each of these vertex contains some superfields, and they have some theta expansions. So there are plethora of ways in which 5 thetas can come from them. And you have to take into account all such combinations and all such terms. And when you do that, you add them all up and you incorporate the plane wave part, you actually get the full answer. So once you do that, you have the full ingredients to compute scattering amplitudes of massless as well as first massive states. So we will compute all the massless, massive 3-point functions for a fixed order. So this is the simplest thing that you can compute. And suppose the pure spinor vertex comes with a normalization capital N, and RNS vertex comes with a normalization capital N RNS, and the relative normalization is some G field for a particular external state. Then what we can do is that we know that the relative normalization is the only one which carries some physical information. So we can set the NPS to be 1 and keep this relative normalization in the RNS formulation. So here we have listed all the coefficients for this RNS and PS for all operators. So the first is A is a gluon and chi is the gluino, B is the small b field, G is the small g field, and chi is the small chi field. So these, of course, were computed long ago by Berkowitz himself. And the point is that this we have to compute again because we were working at a different convention. And so we needed to fix our convention. And I should tell you that these amplitudes are extremely simple so that their momentum and polarization dependence can be fixed without knowing any string theory wall-sheet formulation. So it's a normalization which actually carries a lot of information and a lot of importance for this particular case. So once you have these things in RNS and pure spinor, you can actually use this to fix GA. Once you have fixed GA, you can use this to fix G chi. And similarly, you can use this to fix GB. You can use this to fix GG, and you can use this to fix G chi. But you see that for the massless massive states, we have another relation involving B, another relation involving G, another relation involving chi. So now we don't have any more freedom to fix our relative normalization. So the point is that if we plug this thing that we have already found here and plug this into here, what do we get? And we find that they exactly matches, and which is a completely non-trivial consistency check. And we see that this particular set of values of the relative normalization between pure spinor and RNS, actually you will get all same amplitudes that you compute using RNS and pure spinor, they will completely match with each other. So let me summarize. So we have basically given a systematic procedure to construct massive vertices, and which also allows you to do covariant theta expansion to all orders. And we have explicitly used that theta expansion of the unintegrated massive vertex to establish the equivalence between RNS and pure spinor amplitudes, including first massive states as well. And one question is that we can ask is that we should be able to adapt this construction to construct massive vertices in ADS5 diagrams. What about endpoint amplitudes for massive states? Because now that we have integrated and as well as all these things, we can construct for this higher loop level, which was what Oliver was mentioning in his beautiful talk yesterday. And perhaps it's a more rather lofty goal that perhaps we can give a first principle derivation of this prescription. And also what about off-shell states in pure spinor formulation? Now that we understand the on-shell vertices and its construction a bit better, can we go to off-shell? Since we are out of time, I will just float this slide. This is something that Harold already talked about in the diversity session. There is this website. Please take a visit. This slide is already on the website. You can take a look into it. Thank you, and I hope that all of you stay safe in these troubled times.
Thank you for the very nice talk. Are there any questions, comments? Okay, Mohab, please.
Thanks. Hi.
Hi.
Fantastic talk. So I just want to ask, so Berkowitz and Chandia had this at the first level had this this construction in terms of just one form, this B and its derivatives.
Yeah.
Right.
So
whereas you have all of these other fields, right? So you introduce one field for every field in the multiplet. But using the relations that you showed us, is it the case that at every level you could simplify your formulation and find a formulation like the one they have in terms of a single field, perhaps, and its derivatives?
So let me just tell you this. Right. So the point is that all of the superfields, capital B, capital F, all of them actually represent the same supermultiplet. It's not that they're representing a different supermultiplet or anything. So at this point, it might seem to you that it's an overkill, that why do I need several superfields to describe the same supermultiplet? The sole reason for us to include this is that this BRST equations, this QV equal to 0 that I flashed very quickly, these equations are very difficult to solve if you have the supercovariant derivative sitting around. So at higher and higher massive orders, these equations are going to get more and more complicated. Whereas if you use this formulation where you introduce multiple number of superfields describing the same supermultiplet, but of course they have to be related to each other, because you cannot really describe a single supermultiplet with many inequivalent superfields. So those relations are the ones which actually allows us to cast the covariant derivative of a superfield in terms of linear combination of other superfields. So this actually allows us to, reduce this set of equations from a equation involving supercovariant derivatives to only algebraic in superfields. And that actually helps in solving it. And essentially you can always go back to writing your final vertex in terms of covariant derivatives of a single superfield if you want. You just have to invert the relation that we have. And the reason you can invert it is basically because of this relation that I showed.
Right, but I was just wondering whether perhaps there might be some of single superfields and derivatives that perhaps you're missing or would not be seeing by doing this, this overkill, which is not an overkill. Sorry, you got interrupted a bit. I couldn't hear the question well. Can you just repeat? Sorry, so I was wondering whether perhaps there is some sort of iterative structure in having a single field and its derivatives that you might be missing by introducing all of these extra fields. But I can see that what you're doing is perfect. Yeah, I'm just wondering perhaps there's some structure which we're not seeing in this way. Yeah, there could be some structure, but we spend actually months looking for such structure. Initially we tried to solve this in terms of a single field and its covariant superderivative, and it looked like that the recursive structure that you get from it gets more and more convoluted. Whereas the moment you do this trade-off, it actually becomes much more simpler. So if there is some simplification at the level of a single superfield and its covariant derivative, at least it was not obvious to us for many months that we spent trying to do it. All right. Thank you.
Hi, I have a short question. So yeah. So I guess so here you are at 3 levels, so you're using the minimal formalism for the pure spinor. So can you easily extend it to the minimal formalism to go to one loop, or?
Yeah, right. So I didn't have time to elaborate on this. So even though it looked like that all we are doing is in the minimal formulation, but actually the point is that this vertex works equally well for the non-minimal formulation, because the BRST condition actually doesn't change from the minimal to non-minimal. And for the tree level, actually the 2 amplitude prescriptions completely coincide. They completely match. And for the understanding is that when we go to loop level, we will use this vertex operator to follow the non-minimal amplitude prescription.
Okay, thanks.
Okay, so actually my internet connection was unstable, so I lost the Zoom connection twice during the question time, but this, I'm sorry about this. Are there any more questions?
Yeah, I have a comment.
Okay, go ahead.
Yeah, so this is regarding the question that was asked about introducing one superfield for each of the physical fields. So, I got to know it from Ashok that there is something called renomic formulation of superstring theory, not of
Supergravity.
supersymmetric theory. Yeah, supersymmetric
Supergravity.
theory. Yeah, exactly. And there they essentially do the same thing, that they introduce this uh, each of the field will have its own superfield. So this is one just brief comment. I do not know much about it. So yeah.
I mean, reonomic formulation does have some similarity, but I don't know if it is identical, and definitely they only work for massless states, not massive.
Okay. Yeah, but the key idea that you need to introduce this superfields for each field is kind of identical. So probably the kind of difficulties that, that that was being asked probably will also be present there. And one more thing, probably it's not very transparent, but in Berkowitz's analysis also, there was this capital G field, but in the rest frame, which captured at its zeroth component of theta as the small GMM. And similarly, there was another field, superfield called HS alpha, which was proportional to psi s alpha that we introduced. So it's like, yeah, so it's like to each of the physical degrees of freedom, there essentially were superfields for each of them. Yeah, so this is my comment.
Okay, I think we can officially close the session. You can continue the discussion during the coffee break. And let's thank the speaker again. So actually we are a little bit running late. So maybe we should take 10 minutes break. So they're resuming so 10:50 in Brazil.
Sorry, I just wanted to add something. So
Yeah,
I mean, you can make sure you're not missing something by just comparing with the DDF expression. So, of course.
yeah, exactly. So this is what I was trying to allude to towards the end, that whether one can, I mean, because the DDF construction that Renann has is very robust. I mean, it definitely covers the entire spectrum. So one way to check that whether this prescription really holds for all arbitrarily high massive states would be to do that.
Yes, yes.
I think you can start sharing screen. Share screen.
Has it come up?
I see your screen, but not the slides.
Okay. Oh, it happened last time also.
This is like a Zoom screen, maybe. So. Okay, I see your plan of the talk.
You can see?
Yeah. Oh, not now.
Oh, good. Let me try it again. Oops.
Okay.
Yeah.
Do you think you're ready?
Yeah. Is it visible now?
Yeah. Now I see the plan of the talk slide. Is it okay? Yeah.
Yeah.
I think it's visible. So could you speak a little bit louder?
I'm ready. Yeah.
Okay.
I'm ready.
Now it's better. Okay. Okay.
It's better?
Let's. Yeah. Now it's better. Okay.
Okay.
Okay. Let's start the. Okay. Let's resume the session, and the next speaker is Sitender Pratap Kashyap from HRI. Is talking about the construction of covariant vertex operator in the pure spinor formalism. Please.
Thank you. Yeah. So I'd like to begin by thanking the organizers for giving me this opportunity to present the work that I have been doing with my collaborators, Subhroneel and Lipinski. And currently I am at Institute of Physics. And yeah, so the talk, one more important thing is that we have had a lot of discussions with Ashok Sen during this, all of the projects, and we really thank him for that. Okay, with this, let me begin by telling what is the topic. My topic is to speak about construction of covariant vertex operators in the pure spinor formalism. Thankfully, Subhroneel has done a lot of job in his in his talk. So let me, it allows me to go a little slower. Here is the plan of my talk. So it consists of 3 parts. In part 1, I'll give some facts and spell out some of the basic assumptions that we will be making. In part 2, we will illustrate our procedure by rederivation of unintegrated vertex operators at the first massive level of open superstring. Subhroneel covered it briefly. Maybe I'll present a little more detail perhaps. And then we will apply this procedure for construction of integrated vertex operators. Here, essentially, we will not be very detailed. We will just point out what are the essential new features that arise, and then we will just give the steps of generalization to all massive vertex operators. So part 1. So here, let's start by asking ourselves, what do the string amplitudes look like? So it's given here. So this is like it's a correlator of various vertex operators, and then after that correlator is evaluated, we do integration over the moduli space. We will not be bothered about this integration for this talk. What we are what we are concerned with in this talk is the form of these vertex operators. Now, so VIs are the unintegrated vertex operators, U are the integrated vertex operators, and if we are working at loop level, then there will be insertions of B hosts, and they are done by using Beltrami differential. Okay, so now a well-defined theory is one in which the string amplitude will be free from various kind of divergences. And in this particular talk, the kind of divergences that we will be concerned with so as to avoid are the kind of divergences which are because of the lambda bar lambda inverse powers present in these correlators. So what are the sources of those? The first source for that is the expression of B itself, which has poles in lambda bar. Now, obviously, in the limit when lambda bar lambda goes to 0, this diverges. So one source of this kind of divergence is here. Now, the only other places where it can come from are the unintegrated vertex operators and the integrated vertex operators. So what we want to do is we want to avoid in our while constructing these vertex operators, presence of inverse powers of lambda lambda. Now, the question is, can we really avoid them? The answer is yes and no. Now, why yes and no? Because it depends on how we choose to express our vertex operators. So this particular slide is related to lambda bar lambda going to 0 singularity. So keep this in mind. Now let's turn our attention to how do we really, what are the relations that we can use to construct the vertex operators in the, let's say, unintegrated form. So the unintegrated vertex operators are found by solving for the host number 1 and conformal weight 0 object which satisfy this equation. That is, they are related by the VRST charge QE equal to 0, and these vertex operators are defined up to Q exact piece, which is Q omega. Now, one important thing is that this capital omega, this can be used to eliminate the unphysical degrees of freedom. Now, what are unphysical degrees of freedom? By unphysical degrees of freedom, I mean any degree of freedom which can be eliminated by going to a very specific frame, a special frame of reference. Now, how do we take care, can we devise a procedure in which the unphysical degrees of freedom characterized by omega are eliminated by themselves? The answer is yes. So what is that answer? The answer is that if we really work with exclusively physical degrees of freedom from the very beginning, this implicitly assumes that the freedom because of omega has been taken care of. So this is second important point. So we will work with physical degrees of freedom from the very beginning. Now let's turn our attention to this particular slide in which we consider an equation of this form, which is d alpha on S equal to T alpha. Here S and T are some superfields. Now our goal and our question that we are interested in is, can we remove this d alpha from S? The answer is yes, we can. This essentially is like taking another super covariant derivative and then multiplying with gamma and then multiplying with another p slash, and then we get this relation. So, but here m squared is the mass of that particle or that string. So we see. Now here the important point to note is that this kind of inversion is only possible if m squared is not equal to 0. Now let me conclude what lessons do we learn from the 3 slides that I showed. So the first slide said that the goal of first slide was to avoid lambda bar lambda poles in V, and that can be done by working in minimal gauge, something called minimal gauge. So pure spinor comes in 2 formalisms. One is the minimal formalism, another is non-minimal formalism. I saw also Chandia's slide, and he has some introduction to non-minimal formalism, which you can have a look in the next talk. So and also the cohomology of the minimal and the non-minimal formalism are same. So what we can do is we can work with vertex operators which are in the minimal formalism, and those should avoid this lambda bar lambda singularities. Yeah. The second point is that in pure spinor formalism, there is no natural way of defining the integrated vertex operators. So what we do is we borrow the relationship which relates the unintegrated vertex operator to the integrated vertex operator, which is of 2 types, let's say. So one of them is involving the B host, another is just taking plain action of Q on V equal to del V. Here del V is the world shape derivative. Now, the first form in which B surrounds V, because B has explicit lambda bar lambda poles, so invariably the integrated vertex operator will also have, but the second form Q equal to del V, if V is chosen in minimal formalism, then Q equal to del V will ensure that no such poles are informed. So what we will do is we will use the second form to solve for the vertex operators. Now for the conclusion from slide 2 is that we will work with physical degrees of freedom. But where do we get those from? We get those from, let's say, from the RNA spectrum itself. Now, conclusion for third slide is that our analysis will be valid only for massive states, because for only them this inversion is possible. We'll see where this inversion comes. Subhroneel has already pointed that out. So now let me briefly, very briefly, because Subhroneel also already did describe it, recall the audience with essentially the variables that we'll be working with. So the action for the left movers in 10D flat space-time is given by this, split in two parts, matter and ghost. The matter xm and theta alpha form n equal to 1 superspace in 10 dimensions. Now, in order to work with manifest super space-time symmetry, what we'll do is we'll work with supersymmetric momenta, and these supersymmetric momenta are given by this. Also, this lambda is the pure spinor, and it has this constraint, and because of that, its conjugate variable W alpha has a gauge invariance or gauge transformation, which is like this. And in order to keep gauge invariance manifest, we will work with the gauge invariant objects J and NMN. As Subhroneel told, that this is the Lorentz current and this is the ghost consumption. Now, so the point is that the vertex operator come in two varieties, as we already said. And for the unintegrated vertex operator, the equation which we need to solve is QV equal to del V, QV equal to 0, and then fix V using omega. And finally, after fixing that, we can solve for capital U of integrated vertex operator. In the talk, we shall expand our vertex operators in plane wave basis. And here V hat represents other factors other than e to the I k dot x. And V hat will have conformal weight n, because we demand this total vertex operator to be primary of dimension 0. E to the I k dot x has at a net level of excited open superstring has a weight minus n. So V hat will have weight n, and consequently from this relation we see that U has a dimension higher, so it will have n plus 1. And one very crucial identity for us will be the one which relates the ghost variables NMN, lambda and J, which is given like this. Please keep this in mind. This we shall be making use of. Okay, and so some of the OPs that will be relevant for us, there are so many because there are so many variables, but one which I'll particularly use is this d alpha d beta is phi n. Just keep this in mind. And here also the expression of the super covariant derivative is given by this, as I had used this expression earlier, d alpha earlier, but not given its explicit form. Now here it is. Now let's come to the part 2, where we will slowly go through the construction of the unintegrated vertex operator at n squared 1 over alpha in as Subhroneel already have described. But let's go through it again. Now, states are zero weight conformal primary operators that lie in the Weierstrass homology. Our goal is to find an algorithm to compute conformal primary zero weight operators appearing at first excited level of superstring. In other words, what we want to do is we want to solve for this V dimension 0, ghost number 1, and the integrated vertex operator will be 1 using these equations. Now, the point is the unintegrated vertex operator and the integrated, both of them should be constructed out of these fields. The fields and their conformal weight and ghost number are given here. Only lambda alpha has ghost number 1, rest of them have 0. And the field pi m, d alpha, del theta, except lambda alpha, all of these have conformal weight 1. Now, in order to do that, I must tell that this vertex operator was constructed by Berkowitz and Chandia way back in 2002 and is already well known. We re-derived this to illustrate our methodology, which can be generalized to construct any vertex operator. This derivation I have borrowed from Subhroneel's thesis. At this particular level, the states have mass squared 1 over alpha, and they form a super multiplet which is having 128 and bosonic and 128 fermionic degrees of freedom. So 128 is captured by a second rank and three-form field, GMN and BMNP. So GMN has 44 degrees of freedom because it satisfies these conditions. Similarly, BMNP also has, BMNP has 84 degrees of freedom because of these conditions. And the fermionic degrees of freedom are captured by the tensor-splitter field, which satisfies these conditions, and consequently its degrees of freedom are reduced to 120. Now, we recall that vertex operators are of this form. In the rest of the talk, we'll drop this e to the I k dot x and simply, and also hat over v. So this is what we want to solve for. Now, what is the most general host number 1 and conformal weight 0 operator? This has 6 terms, and all of the objects other than the we will have in each of these terms of this form, in which there will be a superfield which is just function of x and theta. Rest will be like del lambda alpha, del theta alpha, d beta lambda alpha. All of these we will call these as basis. And yeah, so the information about the space-time superfields will be in the superfields like A alpha, B alpha, beta, etc. Now, one more thing is that we can use omega to eliminate the gauge degrees of freedom and restrict the form of the superfields. For example, using some particular form of omega, we can restrict V alpha beta to this form, in which the degrees of freedom will be carried by BMNP. As we can see that V alpha beta, because it has 16 cross 16, which is 256, this reduces to a 3 form because gamma MNP is antisymmetric, so it reduces to 120. So at most this can carry 120 degrees of freedom, but this is further restricted. Now, Berkowitz and Chandia showed that if one solves for QV equal to del V and subject to this condition, one finds the same set that we described earlier. Now, our approaches are a little different. What we want to do is, we do not want to show that at a specific level these are the states. We will rather assume that the spectrum is already known at a given mass level. Our goal is not to show that pure spinor has same spectrum as that of NSR or GS formalism. Rather, our goal is to find a simple, possibly, algorithm that gives covariant expression for the vertex operators. So our strategy is to directly work with physical degrees of freedom, and this takes care of the omegas. It is important to note. Oops. Yeah, it is important to note that we have made of omega already if we work with physical fields. Now, our next step is to introduce physical superfield for each of the fields. So for small GMN, small BMNP, and small psi, we have capital G, capital B, capital psi, and such that at theta equal to 0, the component is given by precisely GMN, BMNP, and psi and alpha. Secondly, we will also demand that all the conditions that small fields satisfy will be satisfied by the capital superfields. For example, psi m alpha. For example, GMN will be symmetry. GMN will be capital GMN will be traceless, etc., etc. Similarly for psi, and similarly for the p-form. Okay, and yeah. Now we expand all the unfixed superfields appearing in the unintegrated vertex operator as linear combination of the physical superfields G, BMNP, and psi. Let's take an example. As an example, this F alpha Mn can be written exclusively in terms of psi. How do we know this? We know this because we can do a rest frame analysis, because this is, and do SO9 group theory, because this is a massive state. So we can always do that. So F alpha Mn splits into two pieces. First is alpha 16 times 9 is 16 plus 128. Similarly, F alpha ij is 16 plus 128 and 432. Here, the ones that are marked in red, we will throw away. So this is, remember, this is like Q, capital Q acting behind the scenes. Okay, so we see that there are just two irreps. So there can be at most two terms. And as Subhroneel told, by inspection, we can write these two terms. Okay. So we repeat this process for all of the superfields. So now we can see using this procedure, we can set A alpha and E alpha to 0, and it is very trivial because this can carry 16 degrees of freedom, and E alpha can carry 16 at most, but none of the superfields are like that. So these two vanish straight away. Berkowitz and Chandia had the same conclusion, but after a lot of gate fixing. Now, so at this stage, what we want to say is that the set of coefficients which enter into the definition of, which enter into the process of writing down the superfields in V in terms of the physical superfields GMN, DMNP, and psi, those coefficients we collectively will call AI. So this is the first level of unknown coefficients that we are introducing in our picture. So keep this in mind, A, the beginning of the alphabets. Now, when we act the VRSC charge on the vertex operator, unintegrated vertex operators, we will get these kind of terms, which will involve the super covariant derivatives. Now, recall in the beginning of the slides, I said that we wanted to invert this kind of relation D alpha. We want to strip this D alpha. We want to strip this D alpha from B, beta, sigma, etc., etc. But before that, the first point is that this H alpha Mn we have already expressed in terms of the physical superfields. So these can ultimately be related to D alpha GMN, D alpha BMP, and D alpha psi n im beta. Yeah. So once again, this D alpha FM beta can now be re-expressed in terms of this. Yeah. So finally, what about these D alpha psi, D alpha BMNP, and D alpha GMN? What about this? So determination of the supercovariant derivative of physical superfield is our next major step. We employ the same strategy. What we will do is we will again do this group theory analysis, this alpha and beta, and then M, and then from this we will take various tensor products, etc., etc., and then figure out how many 144, 44, 84, and 128 are there, and based on that we will write down the structure. So at this stage, what we are doing is we are re-expressing the supercovariant derivative, covariant derivative of the superfields, physical superfields, in terms of linear combination of other superfields. Okay, and this requires introduction of another set of constants. This I will denote by B. Similarly, yeah. For example, for D alpha psi m beta, this is the expression. Similarly, one can write for D alpha GMN and D alpha BMN. And in fact, yeah, so these are the differential relations which will be used for theta expansion, which is very crucial, which Subhroneel mentioned in his talk before. And now writing D alpha in terms of the supercovariant derivative of physical superfields in terms of other superfields introduces second fresh set of undetermined coefficients, which we will call by BL. Once again, the equation of motion will solve using equation of motion, that is QV on 0 will determine these BIs and AIs. But this is not the complete end of the story. There is a further set of constraints which will be introduced, and these we shall collectively denote by CI. Let's see what are these. Yeah. So recall, I had asked you to remember this operator identity between the ghost variables. So this has free index structure n and beta, and these can be so this can be used one operator to in terms of can be used to trade one operator in terms of other set of operators. Note that this is at host number 1 and conformal weight 1. Now, this particular relation generates various kind of identities at various host levels and various conformal weights. For example, it generates this particular identity, and this is at host number 2 and conformal weight 1. Now this can equivalently be written in terms of some Lagrange multipliers fields, which we will denote by K, and let's just give this equation a name by capital K. So capital K's will always represent Lagrange multipliers. Please keep this in mind. Now, once again, our usual strategy, we will also expand the Lagrange multipliers in terms of the physical superfields, and these will introduce these collective coordinate Ci that I told. Now, we are having three kinds of unknowns, AIs, BIs, and CIs. And what we hope to do is we want to solve for all of them, but the only requirement now is that they should be annihilated, that the vertex operator should be annihilated by Q. And also, in order to freely set the coefficient of each of the basis elements 0, we can add this special 0 of the Lagrange multipliers. And after that, we can collect all the terms in QE plus K, and then set each of the coefficient of each basis to 0. And then we'll get some set of algebraic equations in terms of the AIs, BIs, and CIs. Solving these linear set of equations determines all of the AIs and BIs and CIs. And in particular, this will also give the precise differential relations of the physical superfields in terms of other physical superfields. Doing that, we find that the vertex operator is just comprising of four terms, and these four terms are given by this, and this agrees with Vertex and Chandia. Now, yeah, so this methodology is applicable for general other vertex operators. Now, part 3. So let me not go through, because as you can see that it is really straightforward. So what we will do is we will point out the various differences. So for construction of the integrated vertex operator, what we will do is we will solve this particular equation. Now this is at host number 1 and conformal weight 2. U is the only unknown here because we have already constructed. Now this is the major point here. The most of the subtleties that lie are in figuring out the various kinds of identity among the various worldsheet operators that appear at this level. For example, and these we have found that they are of 3 types. Some of the identities follow from the I and beta, the relation between the ghost current and ghost currents. Yeah. So, for example, at this particular level, there will be 6 such identities, and then there are other set of identities which reappear, and these are because these are not at unintegrated or massless level, because, and these are like trivial rearranging of the vertex of the operators on the worldsheet, like d alpha, d beta. This is related to d del m del pi e. This is second kind of constraints, and the third are which are already there and which are identically 0. For example, this GMN is same superfield, that the same physical superfield. This particular operator vanishes at identically. So this kind of surprises we do get, but the point is this: when we were solving it, we were not aware. Constraints that can appear, and they will fall in these 3 of them. Okay, and after solving this, we get our result, which is the integrated vertex operators. To begin with, it had 20 terms, but because of our unsarts, we find that only 10 of them survive, and these are the precise coefficient. Okay, so generalization now is really obvious. So let me just, because I have just a couple of minutes left, I'll just briefly tell the steps. Step 1 is to write down all the. Step 1 is construction of the unintegrated vertex operator, in which we express all the superfields in terms of the basic superfields, which is step 3. Now we find out all the set of constraints, the 3 type of constraints that I told, one set of constraints are obtained by this trivial manipulation of this basic identity, like taking partial derivative of this or multiplying it with various other operators like d alpha, pi m, nm, or j. And then there are these kind of identities which are between the matter sector variables. And finally, we also drop these kind of operators which are identically zero. And then we introduce the superfields also for them, and we re-expand these superfields in terms of the fundamental fields FB, FB. And then we compute QV, and this will require relations of this form. Once again, we re-express this in terms of the physical superfields, and then we solve for QV equal to 0. Now, QV equal to 0 will determine all the coefficients, and we will get the unintegrated vertex operators. Now we are ready for solving the integrated vertex operator, and this can be simply reiterated by QV equal to 10. Yeah. So now let me get back to some applications. The applications are that.
So how many? I think you are running out of time.
This is last slide. Last slide.
Okay.
Yeah. So now, as an application, the differential relations which are required for theta expansion are a byproduct of this procedure, and Subhroneel already explained that. And we also use the integrated vertex operator at first massive level that we found to do some mass normalization computation at one loop for a stable non-BPS state in heterotic strings. And we found, and this is in collaboration with Renann, which will appear. And this result matches with what was computed earlier by Ashok. And finally, there can be a lot of computations done because of this integrated vertex operator at tree level and one loop. And we hope to see that the kind of structural relations or identities that were found at massless level will, for the scattering amplitude, will hold here also. This is in reference to values. With this, I thank you.
Thank you, Sitender, for the nice talk. So we are running out of time, but are there any quick questions to Sitender? So maybe we move to the next talk, and we can hear more about the spinor formalism, and we can discuss later, perhaps. So thanks again, Sitender, for the very nice talk.
Thank you.
Okay, so our next speaker is Osvaldo Chandia from Adolfo Ibáñez. So are you online, Osvaldo? Okay, so.
Can you hear me?
Yeah, now I can hear you. So can you start?
I have a problem. Yeah, I don't have electricity in my house right now.
Oh.
So I need Nathan put my slides for me.
Uh-huh.
Okay.
Is it possible?
Yeah, it's going to take a few minutes.
Okay. So, and my connection is on and off all the time. So I don't know what's going to happen.
Okay. Just give me a few seconds. While I'm doing this, I had a question about the previous talk. Can you use symbolic computation to do any of these steps, or do you need to do them all by hand?
Could we do it symbolically? Nathan, can you once again repeat it?
The question is, can you use symbolic computation to do any of these?
Symbolic in the sense? Symbolic in the sense?
Mathematica.
Oh, yeah. So Mathematica can be used, certainly. And in fact, we had made use of Mathematica a lot during this. And I would like to mention that this requires computation of a lot of OPs. And that can be done with a package called OPDefs. So it readily computes it. And then various other steps can be done in Mathematica. That's all.
just need to open the file.
Bad.
I can it also, but
So my net connection is that as well. So, okay.
so shall we say that we'll start in 5 minutes?
I can.
Okay, so let's, okay. Let's start in 11:30. Okay, is it okay?
Sorry, I can't hear any complete phrase from you.
Okay, one
Okay,
second. So if people want to ask questions during this 5-minute period, that's fine. People can do whatever they want.
Okay, so any questions, discussions for the 5 minutes?
I have a couple of questions for Lionel and Yvonne, if I may.
Okay, please.
Yeah, go ahead. I'm here anyway. I don't know if Yvonne is.
Hi, Lionel.
Hi, good to see you actually for after 10 years.
Right. So one question I have is about B models. So the original written version is a B model. So I was wondering whether, given that you said that you looked at the anomalies and so on, I was wondering whether you thought there was any chance that that there is a B model version which would reproduce which can be defined in ambitwister space and which would do your models.
So with the B model, my view was always that somehow, because the B model strings themselves, they're topological, they don't do anything. And so what was doing all the work in Wissen's model were the D1 instantons. And, yeah. And then my view on that was this,
Well, I mean, when you say when you say they're topological and they don't do anything, it's not really true. They do the complex structure deformations, which is exactly what you want them to do. So it's not
right.
Totally...
But they don't give you the world sheets. I mean, the world sheets are points. And
yes, so yes, you also need the D instantons, but the fact that they're topological doesn't mean that they don't do anything. In fact, they do very precisely what you want them to.
No, sorry. Okay, so they give you the right. That's right. They give you the right moduli. You're absolutely right. And so anyway, my view was that the Nathan's string was really, in some sense, the theory of those D1 instantons. And then I guess I wrote a paper with David, which said that these things were all really beta gamma systems or heterotic models. And so that's my view on what all of these things are. So they're really either to be thought of as Berkowitz style beta gamma systems or heterotic models, if you want to formulate them in that way. So that, yeah. That's basically my view. And then you see that there's a nice paper by Ed Witten on 0,2 half-twisted 0,2 models, where the moduli is precisely the deformations of the background complex structure. And so that really gives it all to you in one coherent model. I don't know if that answers your question.
Right. Well, I mean, I guess if there is a consistent string theory, I mean, I'm still trying to understand whether your models should be viewed as consistent bona fide string theories. It's not obvious to me. I mean, they seem to be mimicking the computation of the scattering amplitudes at tree level, and that's fine. But whether they are actually genuine bona fide string series and so on I think is still a little bit well, still has to be investigated.
So my view would be that they're half twisted, and so they don't have you know, so they're not quite topological. They're sort of they're analytic. That depends on the complex structure of the background. And as I say, there's this very nice paper by Ed Witten from about 13 years ago called something like half-twisted 0,2 models, which sort of explains how you can understand curved beta gamma systems, which is in some sense what Nathan's model was, as half-twisted 0,2 models. Yeah, so I think that's the right category of string theory to think about for these models. Yeah.
And so the other question has to do with, so you said you looked at anomalies, and so you have, you said that you computed the anomalies and that they vanished, but you have gauge fields, and the question is, what is the gauge group?
Yes, okay, so I guess there's two types of anomaly. There's so in the 6-dimensional models, that then we are gauging an SL2, the little group SL2 essentially. And so that there will be gauge anomalies associated with that. But then of course there are also the main worldsheet gravity or central charge anomalies. So it was the gauge anomalies that vanish on the nose, and so that was nice for those models, but only in that format of the super Yang-Mills or the supergravity. You know, if you mess with that, you get something that will fail. And but then the central charge looks like it needs the extra dimensions that would take it up to 10. So it looks like it's really kind of looking to a full 10-dimensional model, as in the original RNS case.
Okay, I think
it's probably time for the next talk.
Okay, I think the share screen is ready. So Osvaldo, are you ready? Please start.
Can you hear me?
Yes.
Yeah.
Okay. Okay, so I'm sorry for the problems. And I want to talk about pure spinor because in curve background. This is based on these 3 papers. One of them was written with Nathan. Next, please. The plan of the talk is that I first review the pure spinor string in a flat background. I assume that almost many of the stuff contained in this part of the talk was already discussed before. Then I will describe the so-called minimal pure spinor string in a curve background. And then I will introduce the non-minimal variables which are necessary to construct the V-gauss in flat space. And finally, construct the V-gauss for the theoretic string case in a curve background. And I will end with some final remarks. Next, please. Sorry, Nathan. Can you change slide?
I think I did already.
Okay. Here it is. So the action is constructed up after saying that x and theta are the superspace coordinates in 10 dimensions are kind of free fields in the worldsheet. The difference between x and theta, besides they're both different, they have different Grassmannian parity. Theta is together with his momentum, P, alpha, and x is alone. This is the action, free action. So in order to have no conformal in order to have central charge 0. So Nathan noted that we have to add pure spinor variables. And that's not the only property that has lambda and omega. It also allows to construct a nilpotent charge. This is the nilpotent charge. And this is to check that Q is nilpotent because of the pure spinor constraint. So lambda is not an unconstrained field. It's constrained by this equation, lambda, gamma, lambda. Here, gamma are the symmetric gamma matrices in 10 dimensions. So simply, Q is declared as BRT charge of the theory, and have to note that omega is defined up to the last expression I'm showing in the slide. So everything depends on omega and lambda, respect the pure spinor constraint and the gauge symmetry for omega. Very quickly, next please. This is a nice part. The cohomology of Q allows you to find the physical states. So it's very nice because you, in only one superfield, you have all the physical information of massless states in 10 dimensions. So the idea is to find so-called unintegrated vertex operator, lambda alpha A alpha, annihilated by Q. And because this state is in the cohomology of Q, is defined up to Q of something. So in this case, is the lambda alpha A alpha is defined up to lambda alpha D alpha omega, where omega is a parameter, a superfield 2, and D is the covariant supersymmetric derivative. So one can solve these equations and find the theta expansion of the superfield A alpha. And what one finds is the physical states are here. A is for the photon and psi the photonic. And higher order terms in theta are depends on A and psi through space-time derivatives. Okay, that's a nice thing. I think but it can be repeated for massive states as it was shown before. Then I think this model is conformal, it's space-time supersymmetric, and has this diversity invariance. Okay, so this is the minimal pure spinor string. Next, please. So the theory has a stress energy tensor, T, but has the property of being annihilated by Q, but there's no big ghost in the theory. Not big ghost in the sense that you have big ghost, for example, in the bosonic string. Once you gauge fix the conformal symmetry, no, it's not the conformal symmetry, the diffeomorphism symmetry, you obtain a big ghost, which by construction is pairs T trivial. In this case, in the pure spinor case, B is not a fundamental field, so it has to be constructed. So it's not possible to do it with the minimal pure spinor variable. So Nathan in 2005 introduces a set of variables, so-called non-minimal variables. Omega hat, lambda hat is a conjugate pair. S and R are also a conjugate pair. They are constrained by pure spinor-like constraints. Lambda hat is a pure spinor, and R and lambda hat has this constraint with gamma matrices. And they have a contribution to the BRT charge of the
I fear we lost him.
Hello. Back.
Osvaldo?
Can you hear me?
Yeah, go ahead.
I'm here again?
Yeah.
I'm sorry.
Okay. Right.
I'm still in this. It's correct.
Okay,
this is the correct slide. So what I had to say is the diversity charge of the theory is given by omega hat R alpha, and the non-minimal pure spinor variables transforms under Q, as I'm showing here. So the interesting part is that this new set of variables do not change the cohomology of the BRT charge of the minimal sector. So I don't have to discuss again about the physical spectrum of the theory because it's the same as before. So what's the role of these non-minimal pure spinor variables? Well, they help to construct the B-ghost. So the next slide, I show you how to describe this non-minimal pure spinor set. I have the action. The action is, again, I'm showing you the minimal part of the action. Are you hearing?
I'm hearing you, but I'm not, now I'm having problems.
Oh, sorry. So let me wait.
Sorry. I have no idea why. Let me try to reload the.
Okay. Okay. I'm in page 6.
Yeah. Sorry. Okay. Here we are. Is that right?
Before previous one?
Okay.
Yeah. That's okay. So now I'm writing the action, the new action. So the minimal variable enters in a trivial manner, Q of something, and the BRT charge is now the minimal contribution, lambda D, and the non-minimal variables contribute with omega hat R, omega hat R. And the complete stress energy tensor now has this form. So the non-minimal variables contributes with a Q of something again. So the next step is to construct the B-ghost. So B such that Q of B is T. So in the next slide, I show you the result in flat space time. Here it is. So it looks simple, but the problem, the complications are encoded in this gamma bar field, which is defined here. So just let me mention that the computation of QB equals T rests in the computation of Q of gamma bar that I'm not showing here. I'm going to show you the result after. But it's not so complicated to get the result. So it has some technical problems, but it's direct, the calculation is direct. Only have to mention that looks like in the B-ghost, omega appears not respecting the symmetry of the omega field. But it turns out that this equation is invariant under delta omega equals to the gauge symmetry I'm showing. And so one could express this B-ghost in terms of gauge invariant combination of lambda and omega. But I'm not doing that in this expression. So now I want to reproduce this result in curve background. So something I didn't mention before is the B-ghost is necessary for computing amplitudes in the pure spinor formalism. So it has to have this property, QB equals T, in order to have a well-defined amplitudes. So now I'm going to curve background. And so in curved background, the construction of the action is more or less parallel to the construction of the action in the flat space case. So we have now superspace coordinates, Zm, representing the x and theta of the flat space. The variable d alpha is now a basic fundamental variable, and we add pure spinors. So z, d, and lambda and omega are the basic variables in curved space background. So the action is showed here for the heterotic string case. The first term is just the generalization of the bosonic string theory with metric G and Carl Ramon to form B. The only difference is now the indices are superspace indices. So the first term of the action is the Green-Schwarz action in curved background in the conformal gauge. So the next terms here are required in the pure spinor formalism to have BRST symmetry. So D enters coupling with the VL band. Lambda and omega enters minimally through the covariant derivative of lambda as defined here. This is the heterotic string. So we have for the right moving sector a contribution from the heterotic string, the heterotic fermions. I'm not going to use them, so I'm just mention them in the action. And finally, there's a Fradkin silent term that couples the worldsheet curvature to the superdilaton superfield. Okay, so in this description, the connection appears in the covariant derivative. The Lorentz connection appears in the covariant derivative of lambda, and is given by this expression I'm showing here. There's a scalar part and a two-form part, a matrix part given by gamma AB. So omega M AB is the normal or traditional Lorentz connection. In this formalism, we also have a connection for a scalar transformation. Okay, so as I said before, the background fields E, omega, and B are constrained by Birstein values. So what do I mean by that? Next, please. So what I should have discussing now is what is the meaning of BRST symmetry in curved background. The meaning is the BRST char Q, lambda D, has to be nilpotent
Sorry, we lost you again, Osvaldo.
So we lost the speaker, right?
Yeah. Back again.
Okay, go ahead.
You come back? Okay. Go ahead.
Yes. How much time do I have? So,
Osvaldo, how much time do you need?
Okay. I don't know. think 10 minutes, something like that.
Okay, go ahead.
So I'm going to be as fast as possible. I'm sorry for all the inconvenience. So what I was saying is BST's charge in curve background has to be nilpotent, and the current, lambda d, has to be conserved. So it was discussed some time ago by Nathan and Paul Howe, and they found constraint on the background. So these are expressed in terms of torsion, curvature in space-time, and subspace, I'm sorry, and H is the exterior derivative of the Karl-Ramon superfield. So I'm not showing all the constraints here, it's only some of the constraints coming from nilpotency of Q. But the thing is, after some Hello.
Yes, go ahead.
Hello.
Osvaldo, go ahead.
Okay, I'm going to continue. So the constraints are I'm showing the constraint here. So T is the torsion, H is dB, and R is the superspace curvature. Some of the constraints can be solved. Some of these components can be written in terms of more familiar supergravity type of constraint superspace by choosing some symmetries that the worksheet sigma model has, like Lorentz symmetry, etc. And for example, T alpha beta A is proportional to gamma. So is H alpha beta A. T alpha AB is it involves omega beta, the scalar part of the connection, and also omega alpha is proportional to the covariant derivative in the alpha direction of the superdilaton. So this model was shown to be one-loop conformal invariant by Breno and myself some time ago, and so this is a summary of the result, the constraints of on supergravity background field. So can you move to the next slide, please?
So you have 5 more minutes.
So in the next slides, I'm describing my. This is a review of the superspace in 10 dimensions that I'm going to skip this time. So now I need the BST transformation of the fields in the action. Although it's a very simple calculation to obtain. How the worksheet super fields transform under Q. So it can be done by doing a simple calculation, as I said before. So Q of C is given simply by this expression, where E alpha M is the inverse of the VL line, and all the remaining terms have this complicated expression. So let me just note that there's a sigma alpha beta in all the transformations with local indices like A or alpha. This sigma alpha beta is a kind of local Lorentz rotation with a parameter that depends on the field spinor. So it happens with all the worksheet field you can construct will receive a Lorentz rotation of this type given by sigma. So for example, Q of P alpha I think it's impossible to continue. Back again.
Yes, Osvaldo, just keep going.
Yeah.
Sorry, I didn't hear.
Just keep going. We hear you.
Okay. Sorry again. So the main point I want to say in this slide is the following. Because of the Lorentz rotation, every field has a Lorentz rotation piece in the BST invariance, BRST transformation. So, for example, lambda has this rotation. So whenever you want to construct a big-gauss-like field, whenever you want to construct a big-gauss-like field, you have to remember that in the big-gauss in flat space, lambda hat appears in the denominator of the expression I showed before. So if lambda alpha transforms with a rotation, lambda hat also has to transform with a rotation. So what I'm trying to say is Q of lambda hat in curved space has to contain a Lorentz rotation piece. So I just assume what is the BRT transformation of the non-minimal fields. So when we can see the next slide, I can show you what is the transformation for the non-minimal sector. So as you can see, there's a Lorentz rotation pattern here in every non-minimal BST transform expression. But it's not possible to just put sigma. I have to add some other fields because Q squared has to be 0. So it turns out that I need this X field, which is almost a rotation, but it's not sigma rotation. So it turns out that Q squared equal to 0 fixes X to be of this form. So one is tempted to just mix X and sigma and call sigma tilde as X plus sigma. So the BRT transformation of the non-minimal fields now look very simple. The transformation are simply the flat space transformations plus a rotation, which is nice. So now I will try to construct a big gauss. In the next slide, but before that, I am showing you here the form of the minimal non-minimal action and the contribution to the the energy momentum tensor and the BST transformation generator. So I'm going to skip this. I'm going to the big gauss. So just to remind you, gamma bar in flat space has this expression. So this is flat space. So in flat space, D transform has this transformation. Omega transform to D. Lambda and R are invariant, and lambda hat gives minus R. So is it possible to keep this simple type of BRT transformation in curved background to get Q of gamma bar having this type of transformation? The answer is yes, but I have to do some field redefinition first. So in the next slide, I'm just showing the result. So the gamma bar in curved background is the same, has the same form of the corresponding gamma bar in flat space. The only new thing that looks like a typo, but it's not, is there's a capital D in the expression for gamma bar. So this capital D is related to the previous D by adding a term involving X. X, remember, is part of the sigma tilde rotation. So in turn, with this particular, with the solution I show for X, one can show that the new D is invariant under gauge, pure spinor gauge transformations, as expected. And the transformation for the fields are very similar to the transformation of the corresponding fields in flat space-time. So the capital D transform like the first term in the transformation is like in flat space, plus a rotation. Everything has a rotation. Omega transformed to D plus a rotation. The non-minimal pure spinor field transformed like in flat space plus a rotation. The only field that doesn't transform like flat space plus a rotation is lambda. So lambda has a new piece, which is proportional, I'm sorry, it's exactly 8 times lambda omega times lambda alpha plus a rotation again. So it turns out that if you compute Q gamma bar, you get the same expression in flat space, replacing all the symbols. For example, pi is now the pi in curve background. The same expression up to a rotation, but this time a rotation in vector indices. Okay, it's incredible simple. You only have to check that all factors lambda omega cancel, and this is the case. Okay, so on the next slide, I just repeat this way of calculation. I show you the big ghost. The big ghost has this expression, and try to verify that QB is the stress energy tensor. So now, because B involves more fields than gamma bar, I have to be worried about, careful with the BST transformation of all the fields. So here you can see pi alpha and what else? And pi A. So pi with vector indices and local fermionic index. So it turns out that Q of pi and Q of omega transform again with a rotation plus something similar, expression, which is the corresponding expression in flat space-time. The same thing happens for pi alpha, the derivative of lambda, a rotation, and an extra piece. Now, note that the extra piece always involves omega. So the only thing you have to worry, to check is when you compute QB, all the factors of lambda omega vanishes. And again, this is the case. I'm not going to show the details. So the next step, my final remarks are this. So the next step is to construct the big Gaussian for type 2 superstring. So I was trying to do that. I'm facing some problems that unfortunately I can't show you in this talk. So I'm going to finish here.
Okay, thank you for the talk, despite the difficulty. So we don't have much time for the discussion, but are there any quick comments, quick questions, comments?
Aldo, can you hear me?
You can hear me? Sorry.
Yeah, can you hear me?
Yeah, please go ahead. But I can't identify you. Go ahead.
Andrei Mikhailov, Q lambda is rotation. Cannot you combine Q with compensating gauge transformation so that the resulting new Q is just Q lambda equals 0?
I would like to have that, but I don't know if it's possible.
You always, all these operators are defined up to gauge transformation. You can modify Q by adding to it some lambda dependent gauge transformation. Remember, there is SO10 plus dilatation.
Yes. So the answer is, I don't know. I haven't tried, but I suspect that it can work.
Yeah, then Q lambda would be just 0 as in flat space. I mean for minimal formalism.
I'm not hearing.
Okay, I think. Okay, thank you.
Okay, okay, so let's okay, we postpone the discussion to the later informal discussion. So let's thank Osvaldo again. And I don't think we have time for the second coffee break. So Nathan, should we continue?
Yes, fine for me.
Okay. Okay, so our next speaker is Tim Adamo from Edinburgh. So are you online?
Yep.
So can you start the share screen?
Is that working?
Yes, I see your slides.
Okay.
So he's going to tell us about scattering in chiral strong backgrounds. Please start.
Okay, so thank you very much. It's of course a great pleasure to be virtually in Brazil today giving this talk. And I'll be talking about some kind of ongoing work with Lionel Mason and Atul Sharma, both of whom are in the crowd, so to speak, I believe, which is partly based on a paper that came out in March, but also a more substantial paper which will hopefully see the light of day in the next month or so. So to begin with, I'd just like to kind of set the stage with a bit of motivation for what I'm going to tell you about. And the first thing is this statement, which is a bit of an imprecise statement, but if we're talking about tree-level perturbative gauge theory in gravity in Minkowski space, I'm making this claim, which is that we know everything. And what I mean by this is that we know basically everything about the tree-level S matrices of these theories perturbatively around Minkowski space. And there's a long list going back to the 80s of people who have written down kind of all multiplicity formulae for scattering amplitudes in gauge theory and gravity and their supersymmetrizations in various dimensions and with various amounts of supersymmetry. And indeed, today, we've heard some talks from Lionel and Yvonne talking about further refining these kind of all multiplicity formulae. And I would argue from the perspective of string theory, if you're a string theorist, you should think of these all multiplicity formulae as providing some sort of important data for the alpha prime goes to 0 limit of genus 0 string theory. And the kind of central motivation for what I'd like to tell you about today is, well, what if instead of talking about perturbative gauge theory and gravity in Minkowski space or in a flat background, what if I ask you to tell me something about the S matrix or analogous kind of on-shell observables of perturbative gauge theory or gravity or string theory in a non-trivial or strong background field? And in fact, we've been hearing a bit about this in terms of talking about string theory in ADS backgrounds or in supergravity backgrounds. And I think it's fair to say that much less is known about massless field theories, even in the simplest strong backgrounds. So if you think about ADS or plane wave backgrounds, so sort of very highly symmetric backgrounds, I think it's safe to say that the state of the art for tree-level on-shell observables of gauge theory and gravity in those backgrounds is only 4 points. So there's really a kind of remarkable knowledge gap between what we seem to know about perturbative gauge theory and gravity in a flat background compared to what we know about in even the simplest backgrounds. And one reason you might not be surprised that that knowledge gap exists is that a lot of these all multiplicity expressions that we kind of know and love in flat backgrounds, they don't come from traditional sort of Feynman diagram space-time perturbation theory. There's some sort of novel methods that generate these formulae. And these could be unitarity methods, things like double copy, the scattering equations or twistor strings, which we were hearing about earlier today. And it's unclear in what way these kind of novel methods extend to strong backgrounds. So the question I'd like to consider today is just, can we make all multiplicity statements about scattering amplitudes or their analogs on any strong background for gauge theory and gravity. And of course, answer is yes, or else this would be an incredibly short talk. And so today we're going to focus on a particularly simple class of strong backgrounds, which are chiral and asymptotically flat. And they're going to be 4-dimensional backgrounds. So, but I just want to, you know, if you zone out for the rest of the talk, I think the punchline is just that compared to what was known before, this is really, really a big step forward, because they're going to be all multiplicity formulae compared to the kind of 4-point expressions that were the state of the art beforehand. Okay, so that's the sort of basic question we're trying to ask. So what exactly are these kind of special simple backgrounds that I'd like to talk about? Well, they're going to be a subclass of what are more generally known as radiative backgrounds. And so in gauge theory or gravity, a radiative field is something that's completely characterized by its free data at null conformal infinity, scri, so scri plus or minus. And so if I take an asymptotically flat gauge field or an asymptotically flat metric in the sense of Penrose or Bondi and Sachs, and I do an expansion near scri in, say, Bondi coordinates, the gauge field has some leading terms which come with some free functions, which I've called curly A naught. This is a complex function, and this is its complex conjugate. Then there's a bunch of subleading stuff, so stuff that falls off faster as you run away out to infinity. Similarly, there's this famous kind of expansion of an asymptotically flat metric near scri plus, where the first kind of non-trivial terms you get are proportional to what looks like 2 free functions. This first one, what I've called M sub b, is something called the Bondi mass aspect, and it's actually related to the second one, sigma naught, by asymptotic Bianchi identities. So there is some independent data in M sub b in general, but it's what you might think of as lower spherical harmonics. So L equal 1 and 0 spherical harmonics, and all the higher harmonics, in some sense, determined by this free function sigma naught. So a radiative field is one where it's completely characterized by the data sitting in these free functions. So in the gauge theory case, this free function curly A naught, and in the gravity case, the free function sigma naught. Okay, so not every asymptotically flat gauge field or spacetime is a radiative one. It might have a source. So in the gauge theory case, there might be some L equals 0 harmonics that aren't captured by this free function, and those would correspond to charges. In the gravity case, you'd have things like mass or linear 3 momentum that aren't sitting in this thing sigma naught. We're going to focus on radiative fields, which are completely characterized by those guys. And in fact, they're not just any old function. They're what are called spin-weighted functions, which means that they're best thought of as kind of sections of line bundles over the sphere of generators at scri plus. But if those words don't mean anything to you, then you don't need to worry about them. So, okay, so we're going to be talking about a special subclass of these radiative fields, which in the gauge theory case are characterized completely by some free spin-weighted function A naught. In the gravity case are completely characterized by some free spin-weight 2 function sigma naught. Okay? Now, if I'm talking about a Lorentzian real field, this A and its what I called A bar in the previous slide, they're related just by complex conjugation. Similarly with sigma and sigma bar. So there are no non-trivial chiral field configurations in Lorentzian real signature, because if I set one of these guys equal to 0, I obviously set its complex conjugate equal to 0. If you complexify, or equivalently, if you were to Wick rotate to Euclidean signature, then A bar is actually an independent complex function, which I'll call A twiddle. Similarly, sigma bar becomes an independent complex function, which we could call sigma twiddle. And now these guys are just completely independent. And so we can set one of them equal to 0 without killing the other one. And so the definition of the perturbative backgrounds we're going to be talking about are these self-dual radiative fields. So these are radiative fields for which you've killed one of these degrees of freedom, the one that I've called twiddle. So A naught twiddle or sigma naught twiddle. And it can be shown that all such radiative fields are in fact self-dual in the sense that they're, in the gauge theory case, it's field strength, the self-dual 2 form in 4 dimensions, or in the gravitational case, its Weyl curvature tensor is self-dual. So why are these kind of backgrounds a good starting point to try to find some all multiplicity formulae for scattering amplitudes? Well, it's a well-known fact that this self-dual sector of gauge theory and gravity is integrable. And so there's some hope that we might be able to exploit this classical integrability that's underlying these backgrounds to compute the tree-level S matrix of gauge theory or gravity. Okay, so that's the basic setup. Now, I should emphasize, because we've assumed that these are asymptotically flat, we can expect, at least at tree level, the S matrix to be well-defined, asymptotically flat and source-free. Okay, so we want some sort of formalism that brings out the kind of underlying integrability or triviality of the self-dual sector. And surprise, surprise, the formalism that's going to do that for us is twistor theory. And we've heard a bit about this earlier today, and in Yvonne and Lionel's talk. And so I'm going to give you the world's quickest, least complete introduction to twistor theory. So if you've never heard of twistor theory before, buckle up. But hopefully this will make some sense. Basically, for my purposes, twistor space is just going to be an open subset of CP3, the 3-dimensional complex projective space, which we can describe with homogeneous coordinates, which I'll call ZA. These are just 4 complex numbers, which I've split into 2 sets of 2, so 2 Weyl spinors, mu alpha dot, and lambda alpha of opposite chirality. And they're identified up to overall C star rescalings because they're homogeneous coordinates. So there's only really 3 complex degrees of freedom sitting in here. And the open subset we're going to consider is just the open subset where the 2 homogeneous coordinates lambda alpha are never vanishing. And the basic idea behind twistor theory is that there's some correspondence between this complex projective space PT and a complexified Minkowski space, which is just C4, which is that any point in complexified Minkowski space corresponds to a linearly embedded holomorphic Riemann sphere, which I'll call big X, sitting inside this twistor space. And this correspondence is just captured by the algebraic relations that when I fix an X, the homogeneous coordinates mu and lambda are related to this equation. And hopefully you don't have to stare at that too long to convince yourself that this is the equation for the linear holomorphic linear embedding of a Riemann sphere inside of CP3, or in particular inside this open subset of CP3. Okay, so twistor theory is some non-local correspondence between Minkowski space, complexified Minkowski space on one hand, and a 3-dimensional complex projective space on the other. And it's non-local because a point in Minkowski space corresponds to an extended object, this line, this holomorphic linearly embedded CP1 in the twistor space. And if you've followed this story, of course, you'll know that twistor theory has many, many applications to the study of perturbative quantum field theory in flat backgrounds. And in fact, again, we've heard a lot about this morning already from Lionel and Yvonne. You can encode all massless free fields of any integer or half-integer spin in terms of cohomology on this twistor space. That's something called the Penrose transform. It's known that you can use configurations of points in twistor space to give a kind of constraint-free representations for on-shell kinematics in 4 dimensions. That sort of flies under the banner of something called momentum twistors, if those words mean something to you. But also, twistor theory has already been used to provide 2 of kind of the best examples of the all-multiplicity scattering amplitude formulae I was alluding to at the beginning. So we have expressions for the full tree-level S matrix of n equal 4 super Yang-Mills in 4 dimensions, which are written in terms of holomorphic maps from a Riemann sphere into this twistor space. And similarly, expressions for the full tree-level S matrix of n equal 8 supergravity in 4 dimensions, again written in terms of holomorphic maps from the Riemann sphere into this twistor space. So I'll return to this in a minute and show you some formulae which make that concrete, but I just want to emphasize that twistor theory stuff, it's not so it's already proved its use on flat backgrounds, and now we just want to find a way to use it on these kind of curved self-dual radiative backgrounds that I was describing before. Okay, so the name of the game is we want some way to use this twistor theory to sort of trivialize the self-dual sector, which we're going to be perturbing around. And it turns out that there are sort of these two theorems, which you could think of as like the greatest hits of twistor theory from back in the 70s that tell you exactly how this happens. So the first is due to Richard Ward, and it states that there's a one-to-one correspondence between any self-dual Yang-Mills field on complexified Minkowski space, and here I've said that the gauge group is SUN, but really you could pick any gauge group. And the statement is that every one of these self-dual Yang-Mills connections in 4 dimensions corresponds to a holomorphic vector bundle living over twistor space, with the condition that this vector bundle is topologically trivial whenever I restrict it to one of these lines that corresponds to a point in Minkowski space. Of course, there's some other technical conditions here which make the correct gauge group come out. So in the case of SUN, this vector bundle has to come with a positive definite form, and its determinant line bundle has to be trivial. But that's not going to be terribly important for us. And then, of course, there's an analogous statement for gravity, which was actually published before the Ward's theorem. And this is just that there's a one-to-one correspondence between 4 manifolds with a self-dual conformal structure and integrable complex deformations of twistor space, of this open subset of CP3, where, and this deformed twistor space we'll call E curly T. And the condition is that in this deformed space, there's a rational curve, big X, whose normal bundle takes a specific form. And then if that's true, it's actually, you can, Codera-Spencer theory implies the existence of a 4-parameter family of these rational curves. So the underlying twistor correspondence survives. For every point in a self-dual or a suitably convex neighborhood of a self-dual 4-manifold, there's a corresponding rational curve in this formed twistor space with normal bundle of this form. Okay, so these two theorems are the kind of thing that are going to be running the show in terms of how twistor theory trivializes describing these self-dual radiative backgrounds. Okay, so if the words in those theorems all kind of went over or under your head, let's talk about what they mean in real money. So what's the upshot of this statement? The upshot is that the self-dual sector of gauge theory or gravity is described by some integrable complex structure on twistor space. And in the gauge theory case, it means that there's some partial connection, D bar, on this Ward bundle, this bundle E over twistor space. Locally, you can just write as the flat trivial complex structure plus some gauge potential. And the theorem tells you that this partial connection is nilpotent, squares to 0. And similarly, in the gravitational case, it's saying that the tangent bundle of the formed twistor space comes with complex structure, which again, at least locally, we can write as some finite deformation of the sort of flat complex structure on CP3, such that its integrable or its Nyenhuis tensor vanishes. Okay, so really what these theorems can be boiled down to is just saying that you have some literally integrable complex structures on twistor space. And it's a remarkable fact that for these self-dual radiative fields, which are precisely the ones we're interested in, these connections or complex structures can be in a form that makes it clear that they are sort of tautologically holographic. They only depend on the asymptotic free data which defines the self-dual radiative field. So in the gauge theory case, the kind of connection not one form on twistor space is given by a U derivative of the free function scry, curly A naught, and then its form component points only in the anti-holomorphic lambda directions in terms of the homogeneous coordinates on twistor space. And similarly, the vector valued 0, 1 form that defines complex structure on the curved twistor space, this is also proportional to the free function encoding the radiative data scry for a self-dual radiative space-time. So again, just to emphasize the upshot of all this twistor theory is that you can describe any self-dual radiative gauge or gravitational field by some complex structure on twistor space with a very specific form that's completely specified by the underlying free asymptotic data. Okay? So for most of the rest of the talk, I'm just going to zoom in on the gauge theory story because that's a little bit simpler, a little bit easier to understand. And I'm going to make an additional assumption, which is that our self-dual radiative gauge field is actually valued in the Cartan subalgebra of whatever gauge group we're hoping to study. And this just means that you can think of this, this background as effectively being kind of abelian. But I want to emphasize that it doesn't mean that the S matrix for Yang-Mills theory on this background is trivial, because generic gluon perturbations will have generic color structure, and they will, it just means that with respect to the background, they just have some kind of effectively U1 charge, but they will still interact nonlinearly with each other. Now, you'll recall that, or maybe you won't, I said that this holomorphic bundle E, which lives on twistor space and describes the self-dual radiative gauge field, it has to be topologically trivial when I restrict it to any one of these twistor lines, which corresponds to a point in Minkowski space, or complexified Minkowski space. But it turns out that we can make it holomorphically as well as topologically trivial by finding a frame. So this is some frame on the bundle, which I'll call H, which trivializes the complex structure, D bar, pulled back to each line. And equation for that is just this first one here, where this A is just the partial connection not one form pulled back to the line. Now, it follows that this pullback is actually cohomologically trivial, because the cohomology group that the pullback has to live in vanishes. So that means we can write this A pulled back to the line as D bar of some Cartan valued a function G on the spinor bundle, essentially. And that means that this frame solves this equation when we just write it as the exponent, or the exponential, basically, of this function G. And here, the exponential is understood as the exponential map of the gauge group. So this frame H gives an explicit holomorphic trivialization of the bundle underlying the Ward construction on each line labeled by X in twistor space. Okay, and you can recover the space-time gauge field itself from this splitting function G just by virtue of holomorphicity and Liouville's theorem, basically. So this equation is an elementary consequence of the fact that the connection is integrable and something that you pulled back to the line from twistor space. So if I take a space-time derivative of this function G, I get one term that is essentially the self-dual radiative gauge field, and plus some other term that's proportional to lambda. Okay, so if I was to contract both sides of this equation with lambda on the undotted spinor index, I would read off I would isolate this first term, and I would read off what the space-time radiative gauge field was. So in some sense, this is how you work through the consequence of Ward's theorem for these Cartan-valued self-dual radiative gauge fields. And similarly, gluon perturbations on this background are encoded by cohomology with values in the endomorphisms of the holomorphic vector bundle in twistor space. And so I don't want to dwell on this for too long, but if these kind of formulae mean something to you, you can be very explicit about how you do this. So remarkably, you can just take the twistor representative, say, for a positive helicity gluon, to be exactly the same one you would use for a momentum eigenstate in a flat background. But this thing is now viewed as living in the endomorphisms of the Ward bundle E. And so when you transform it to a field on spacetime, you have to untwist the cohomology to get something that you can integrate. And you need to use that holomorphic frame H to do that, and that does something non-trivial. So the actual gluon field you get on spacetime is not just usual positive helicity polarization tensor, which would just be the first term here. you pick up some non-trivial background dependence. So you like the polarization and momentum of the gluon as it moves through the self-dual radiative gauge field gets dressed. And this E is just the charge of the gluon, so of its color structure T, with respect to the Cartan valued background. Okay, so, all right, I've just given you some big formalism dictionary. The question is, how do we use all of this to actually compute something? And the idea is that we're gonna take our lesson from what happened in a flat background, which the lesson is essentially that tree-level Yang-Mills amplitudes are meant to live on rational holomorphic curves in twistor space, and helicity configuration of the amplitude is related to the degree of that rational holomorphic curve. So in particular, an n to the k MHV amplitude is meant to live on a curve of degree k plus 1. And here I've just written heuristically how you would write a holomorphic map from a Riemann sphere with homogeneous coordinates sigma to twistor space of degree d. And the output of all of this is a beautiful formula known as the RSVW formula, which gives the color-ordered n to the d minus 1 MHV amplitude, and I've written this in a supersymmetric formalism for n equal 4 super Yang-Mills. And I don't want to unpack much what this formula actually means, but you can prove that it's correct. So with BCFW recursion, for instance. And it's clear that this is not a formula that has anything to do with Feynman diagrams. Right, this isn't something you would ever guess just by plunking away with the Yang-Mills, Lagrangian, and Feynman rules on space-time. So, well, where did that formula come from? Well, as we've heard alluded to over various of the talks today, it arises actually as a correlation function in a worldsheet theory, which is called twistor string theory. And so I've sort of heuristically written this here. These ghosts are important, but I've not written them out. Some worldsheet current algebra, and then there's a term which enforces holomorphicity of the map Z to twistor space. And the idea we want to do is to couple this theory to the background gauge potential on twistor space. And that coupling occurs with a term like this. You have some vertex operators where this little a is a cohomology class on twistor space. It's representative for this Penrose transform that I described earlier. And then the conjecture we're going to make is that n to the k MHV amplitude on a self-dual radiative background is given by a worldsheet correlator in this twistor string theory, background coupled twistor string theory, degree d equals k plus 1. So we're saying that the thing that worked on a flat background, we're going to conjecture that it also works on one of these self-dual radiative backgrounds. And I should emphasize, you might worry that coupling to this background introduces some new anomalies into this theory, but it doesn't, because of the fact that this A is a partial connection which is holomorphic. So that big D bar squared equals 0. That means that the potential anomalies you might pick up actually vanish. Okay, so what happens? I have some degree D map from a Riemann sphere to twistor space. I have my partial connection pulled back to the degree D curve. And again, there's a cohomological argument which tells you that this has to be trivial, so it has to be written as d bar of some g. So you should view this splitting function g, and it's valued in the Cartan subalgebra of the gauge group. You should view it as sort of background data. And the result for the correlator is the following. So this factor is familiar from that RSVW formula I wrote down for you earlier, but I haven't been able to do any of the moduli integrals. And there's some universal exponential factor that looks like this and includes explicitly the background data. So the conjecture is that this object for any n represents the n to the d minus 1 MHV color ordered tree amplitude of Yang-Mills theory on a self-dual plane wave background. So that's the output, that's the answer that we're proud of. So you may say, well, geez, okay, you wrote this formula down.
Can you try to wrap up your talk?
Yeah, of course, we're almost done, don't worry. So this formula passes many checks. The most non-trivial ones are that its flat and perturbative limits are correct. And we can actually prove it in the d equal 1 case. We can prove that the formula is correct. There are these important differences from RSVW that you can't do any of the moduli integrals because of the generic background functional degrees of freedom, But the number of integrals that are in the game are still better than the number of integrals, fewer than the number of integrals you'd expect from space-time perturbation theory. And there's a similar but much more complicated story for gravity on self-dual radiative backgrounds as well. So here we are, we have our all-multiplicity formulae that we were looking for. And I just want to conclude by saying, is any of this of use or interest to you if you're a string theorist? Well, there's a special class of these self-dual radiative backgrounds, which are just self-dual vacuum plane waves. These vacuum plane waves are string backgrounds because all of their higher curvature invariants vanish. So I would argue that this formula actually provides data for the alpha prime goes to 0 limit of the massless sector of strings in plane wave backgrounds at any multiplicity. So it's some answer that could be checked or used to check the consistency of curved background string calculations. So in any case, I'll wrap up there with a list of kind of interesting future questions. So thanks.
Thank you for the very useful talk. So are there any, actually we are again running out of time, but are there any quick questions? Raising hands or? Okay, so I was interested in that part of that. So you're saying that it is related to the alpha prime zero limit of plane background?
Yeah, so it's just the statement that there's a special case of the formula I showed you, which is for any self-dual plane wave, vacuum plane wave background. And these vacuum plane waves are string backgrounds. So one should be able to obtain that formula, or at least so you should be able to, certainly be able to obtain the 3-point version of that formula from string theory. If you knew vertex operators and a world sheet correlator prescription for your string theory in that background.
Thank you. That sounds interesting. Okay, so let's thank Tim again, and we move on to the last speaker. So Renann Lipinski Jusinskas from, are you there?
Yes, I can hear you. Can you hear me well?
Yeah, please.
Yes. And can you see my slides? Yes, okay.
Okay, I see your slides. Okay, please.
Okay.
So let me introduce your title, the Chiral strings and their Vertex operators. Please start.
Yes. So this talk is based on this work from last year. There will be nothing fancy about it, just some slightly new additions. So I hope you enjoy. I hope you're not too hungry or too sleepy, depending on where you are. So this is the outline. So I will use the bosonic ambitwistor string as a guide model to go to this construction, because it's easier, but the construction can be easily extended to other formulas, or more interesting cases like spinning string or pure spinors. I will focus on this zero momentum cohomology analysis because it includes something that I'm calling tensor deformation. Yes? So I'll move on to some geometrical interpretation, or how can I determine this BRST charge from some gauge fixing. And then I'll try to motivate how to build left and right movers from the purely chiral string. And I'll finish with some prescription for 3-level amplitudes and some small example. Yeah. So bosonic ambitwistor string, you've heard a lot about it today. So it's basically a chiral string model that gives you a stringy origin for the CHY formula. The action is very simple. So you have here some space-time coordinate xn with its conjugate, and it's purely holomorphic. You have the usual Virasoro ghosts here with central charge -26. And you have this extra ghosts here, and they are imposing this extra constraint in your theory. So it's a by construction, it's a massless theory. So all the spectrum is going to be massless. And you see here it has the usual, well, expected form for a bosonic string. And the physical spectrum, very surprised me, was not very well understood at first, and only 2 years ago, Nathan and Mateus, they were able to show that, in fact, for the bosonic string and the heterotic models, you get a massless spectrum, but with higher derivatives. So the effective field theory involves higher derivatives, so it's non-unitary. And you might wonder how to define these integrated vertex operators, since it's a chiral model, but you've seen already from Lionel's talk today, or Yvonne, that you have this localization operator that you can use to define the integrated vertex operator, and this one gives you precisely the localization of the C5 formula. Also, as Lionel mentioned, there's no clear picture of whether the Ambitwister string is a tensionless or infinite tension limit of the string, because it's a massless theory by construction. So you can think of it as some alpha prime going to 0 or supergravity limit of the string. But also, if you take the infinite tension limit, you get all the fields to be massless. The thing is that there's an infinite number of them. So what I'm trying to show in this talk is that you can see Ambitwister string as this 0 tension limit, but in a very special gauge, in a singular gauge in the worksheet. So let's look at the background. It's very curious that in chiral strings, usually turn on the backgrounds by deforming the BRST chart. So if you look at the action here, for example, there is no space-time metric. The space-time metrics appear here in the BRST chart, right? So if you turn on some background, some graviton background, for example, it will not appear here, but it will appear here. It's like some heuristic argument. But in any case, you can always deform the BRST chart and also redefine your worksheet field so the action is free. So, which is very nice because then you can compute anything very easily. One thing that I'm interested here now is the zero momentum cohomology. So you can think of this one is the most simple state that you can imagine, and in fact it was firstly associated to the graviton state. Sorry, there's some polarization missing here. But there's another one that I'm calling tension field. I don't think it has been explored before, but it's something very simple. It's an extra state in the zero momentum cohomology that's a scalar. Right? And as I showed you, you can think of this zero momentum cohomology as a background, and you can study the string in these backgrounds by deforming the BRST chart. And how can you do that? You can simply act with the B ghost, the -1 mode, in these operators, in the vertex operators, and you get these expressions. You see this one is already the p-square term that appear in the BRST chart. And if you turn it on, it's basically some constant metric background imposing p-squared. But this one is more interesting because of two reasons. So first one is the dimension. If you compare the dimensions of these two vertex operators here, you see that there's a natural length parameter being introduced, or you can think in terms of the string tension T. Note that one is the inverse of the other. And what does it mean? So this expression as a tensor deformation of the Ambitwister string, right? So this is the bosonic, the BRST chart of the purely bosonic case, and this is a Madden tension. The interpretation is more or less simple. So instead of having the p-square equals 0 constraint, we have this edge. So it's p-square plus TDX squared. Yeah? And by construction here, there is this kind of symmetry, T going to minus T. You can see from here. And it turns out this is the symmetry of the spectrum already. Because as I'll show you, this is not only a massless theory anymore. So if you go to the physical spectrum, in the massless sector, you have the usual dilaton, B field, and graviton. You can see this equation of motions in Bolchinski's book. You get the signs and everything. And it's very nicely reproduced there. But in addition, you have a massive spectrum. So there are two states. As I told you, there's a symmetry between T and minus T here. And you get two spin 2 fields. These are the equation of motion. And if you field to associate it to something, you can think of this as the first massive level of the open string. But that's not important right now. And it turns out that you can give this BRST charge some geometric interpretation. It comes from gauge fiction, the first order Polyakov action. So this action, this first order is written in this form, where E plus and E minus are just Lagrange multipliers for this constraint, P plus dx squared and P minus dx squared. And this action, although it is not manifest, it has reparameterization symmetry. And you can fix the gauge like this. This is some, or beta is some parameter greater than 0. This was proposed by Siegel some time ago for the curved strings. And it's just a family of gauges, let's say. But it turns out that any finite B can be associated to the conformal gauge beta equals 0. It's very easy to redefine your worksheet coordinates to give you the conformal gauge. However, there's a singular gauge when you take beta goes to infinity. And that will give you exactly the free action that you had for the bosonic Ambitwister string, plus the BRST charge deformed by this tension that I showed you before. Yeah? If you want to picture it, you can write these two Zweibeins, or the two lectures of Zweibein, in terms of the worksheet metric, and it gives you like these, where sigma plus and sigma minus are just like cone coordinates. Sorry for the picture, is not well centered, but basically you get this picture here. The white plane that you see here, or rho equals 0, is just beta equals 0. And then as you increase beta, you're inclining the plane, and when beta goes to infinity, you get this perpendicular plane here with sigma plus equals 0. So in terms of worksheet dynamics, it means that the only coordinate that matters is sigma plus equals 0, because these two coordinates, they become degenerate. And then you can ask, once I have this singular gauge, can I put it there the left and right movers? And it turns out that because of this tensor deformation that I told you, you can do it. First of all, you can redefine your worksheet goals, C and C tilde in terms of C plus and minus, and the same for B's. And when you do that, there's a natural rewriting of the BRST charge. You have it in terms of two sectors, plus and minus, and they basically don't talk to each other. They are independent sectors. And the BRST charge can be written like this. So there's this familiar bosonic-like form. T plus and T minus are BRST exact operators, and you can write them like this. Right? So you have, instead of P square here or P dx, that would be the Angel-Momentum tensor, you get this combination with P plus TDX and P minus TDX, right? And then you can ask, okay, how do I recover the other, the energy momentum tensor and the H field that I had before? So the energy momentum tensor is very easy. You just take the sum of these T plus and T minus and you get the total energy momentum tensor of the theory. But then there's another one, the constraint that I had before, P squared plus dx squared. So you just take the difference of these fields, multiply it by the tension, and you get this constraint here. And the ghost part is just for the closure of the gauge algebra. And this example can be extended to several cases of interest, like the spinning string with n equals 1 or n equals 2 worksheet superstring with the pure spinor superstring type 2 heterotic, or purely bosonic models in D less than 26 dimensions, but then with current algebras. And this one in particular gives rise to the df squared plus n mu's theory that you heard in Oliver's talk, and that's appearing very often now in these double copy constructions of amplitudes. If I have time at the end, I can give you more details about this. And in all these models, if you have the right conditions, they have gravity excitations, either type 2, heterotic or bosonic, with or without ghosts. By that I mean that these extramassive fields that you see in the spectrum, they are usually seen as ghosts because if you look at their effective action, they have the wrong sign in the kinetic terms. And then how can you build vertex operators in this construction? Unintegrated ones are very easy. You just take conformal weight 0 goes number 2 operators and write them like this. So U plus are operators written from the plus sector, U minus from the minus sector, and X here is the only thing that's a bit exceptional because X does not belong to any sector in particular. Integrated vertex operators are a bit harder because if you use the usual recipe from string theory and you act on them with the B ghosts, what you get is something with the wrong conformal weight, and it's holomorphic. So if you try to integrate this over the worksheets with Z and Z bar, you get something infinite. And this is where the delta bar introduced by Mason and Skinner comes in. But here it doesn't work anymore because Kp, that's the argument that they had before, is not BRST closed anymore. So this expression with this tensor deformation of the BRST charge will not work. So what we want now is some kind of operator delta bar, generalized, such that if I build the vertex operator like this, will give me something that's an integration over the model. And we'll see how it works. So basically we use this age operator in the -1 mode and introduce some extra parameter alpha here. And this will enable us to define left and right movers. If I formally define the operator like this, it's nice because it will artificially introduce the anti-holomorphic dependence. And you can think of it as some analogous to the worksheet translations. So that would define with the energy momentum tensor. Now we define something with h-1, right? But then it's a bit tricky because this delta bar, it acts differently on operators of different sector. So it sort of introduces point splitting. Operators with O plus from the plus sector, they will get translated to this coordinate Z plus, and from the minus sector, they will get translated to the coordinate Z minus. Right? So this is the role of this operator delta bar. It's BRST closed for sure because age is BRST closed or exact in it, and it will introduce this point splitting. And as I said, the only non-trivial operation should be on X because X does not belong to any sector. So whenever I act, I'll define this X bar as the delta bar action on X. And it turns out that it satisfies this very simple equation. Right? So it reminds you of the usual worksheet scalar from second order actions. Right? And in fact, it behaves even more similar because if you compute this OP, this is a complicated operator, it's expanded in a series because of that exponential of delta bar. But then if you compute the OP, it satisfies this very simple one. And the only subtlety that appears here is that the plus sector and the minus sector, they have different sign. So this was already observed by Sigo in his papers that you can see these chiral strings with the sign flip in the XOP. But it's nice because you can check for consistency that it gives you the Ambitwister case in the tensionless limit. So let's say you act with delta bar on the eigenmomentum state, you get this one in the tensionless limit. And if you think of the alpha integration as if you think about the alpha integration, this operator here works as a representation of this delta bar of Kp from Mason and Skinner. So how do the vertex operator look like with this delta bar is very simple. Since it's BRST closed, you can just multiply everything and it will be business as usual. So there is this sector splitting here, operators from U plus, from plus sector and minus sector. X will be transformed to this X bar, such that in the limit of alpha goes to 0 or the parameter or tension goes to 0, I recover this vertex that I had before. And the integrated vertex operator will be defined like this as well. So there will be the usual recipe from string plus this delta bar operator, plus one multiplied. But then at the end, when you analyze the BRST transformation of V, what you get is something like this. So Q of V is the plus of something plus the minus of something. So it looks like the operator that we should have. So what about three-level amplitudes? I will use the usual amplitudes from string. I have 3 unintegrated vertex operator, and I'll multiply by, I'll add here n minus 3 integrated vertex operator. So for this part here, it doesn't matter if I use U bar or U, because as I'll tell you that this is Möbius invariant, so I can choose Z plus and Z minus to lie on any point of this new worksheet, let's say, and I can even make alpha goes to 0, so I'll get this one. And these V's are just the integration here over this Z and this alpha, the alpha, that's the parameter that I introduced for every vertex. And if I want to write in terms of this Z plus and Z minus coordinates, I just do the coordinate transformation here. And this factor of tension will appear from the Jacobian of the transformation. I just left it here because it's important, since if you can imagine that if t goes to 0, this is ill-defined, but it turns out that Z plus and Z minus, they degenerate in the limit. So Z plus equals Z minus when tension equals 0. So if I think in terms of this sign flip OP, it's very easy to compute this AN. But there's another way that's more similar to the Ambitwister construction. So again, if I look at the path integral here, I'll see that the equation of motion for Pm is given by this one. Right? So there are the three unintegrated vertices, and this comes from the integrated vertices. You see the point splitting here. There's a half and there's a point splitting. And on the Renann sphere node, there's a unique solution for this. So it's very similar to the usual Ambitwister business. But this one behaves a bit different because there is like half of the momentum in this Z minus coordinate, Z plus coordinate, and half of the momentum Z plus. But in any case, it's very simple. And then if you put this solution back into the amplitude, what you get at the end is this one. And here you can see the outcome of the plus and minus sign. Usually you have Z plus and Z minus multiplying each other. And now here they are dividing one over the other. Yeah, so this is the influence, let's say, of the sign flip. You can compute this amplitude. It has Möbius invariance, but you can see that it's not very well defined because there are several branch cuts, because it's not multiplying anymore, they're dividing. And you can compute this only for very specific values. Basically, this one here has to be an integer. But then you can use some kind of adapted KLT plus analytic continuation. I have here quote unquote because, as I said, it's only for some points it's defined. It's not that for a region and I can extend the region, but it's just for some points. But if I do that, I'll get a finite number of poles, and this is compatible with the finite spectrum. So I have here a very simple example. 4-point amplitudes, they would have this form here. And this is basically restricted by the form of the vertex operators. Remember that e to the ikx does not have any conformal weight anymore. So all the conformal weight comes from the worksheet operators, and this is very restrictive on the form of these powers here. And these ones come from the sign flip OP. And then if you compute this, using you have the usual understand variables S, T, and U, you get to this form. Right? And then you can check, given these constraints and the same one for n bar plus n bar, you see that this formula here has only poles when S, T, and U are equal plus or minus 1 or 0. That corresponds to the spectrum that you had before. Okay. So just some final remarks. Ambitwister string, as I mentioned in the beginning, it's not clear whether it's alpha prime going to 0 limit or alpha prime going to infinity. But in this construction represented, it's a tensionless limit. So it means alpha prime going to infinity. That you would expect from string theory that you have also an infinite spectrum, but in addition, you have a singular metric gauge. That's why the spectrum is truncated. This construction enables the definition of the integrated vertex operators directly from the chiral model. So although we don't have a full worksheet, let's say, because all the fields are holomorphic, you can reintroduce this parameter alpha that I showed in an artificial way that will give you the right construction for this integrated vertex operator. And they will produce this chiral amplitudes from Siegel and collaborators, or or from Misera and intersection theory that they introduced. About loops, I think it's a bit subtle. A lot of people discussed this already. And modular invariance is very unlikely. If you think of this XX OPE with the sign flip. But again, since this is, I'm trying to map the chiral string to this construction with the sign flip, there might be some subtleties, and maybe there's some alternative prescription to define it on the chiral side only. I don't know. This thing here, you can think of it as some string field theory construction, because if you analyze the spectrum in the tensionless limit, it will give you higher derivatives. But then if you go to the fine tension, everything's okay, except that you have the introduction of ghosts. And it turns out that these ghosts, they work as auxiliary fields, and when you integrate them out, you get to these higher derivatives. I can show you a slide about the S square plus MUs if there's time. And there's another subtlety that has to be understood is that I told you that there is this symmetry between T and minus T. And this happens even in the adjoint model for either bosonic string, or either pure spinor string or the spinning string. You have, in principle, have space-time supersymmetry plus tokens, and that's a subtlety there. It might be very easy to understand, but I still don't know the answer for this. And that's all for today. Thank you.
Okay, thank you, Renann, for the very intriguing talk. So, are there any questions, comments?
I can ask a question. Renann, at the beginning, you said there was an extra scalar state in the cohomology.
Yes.
Was that not described in my paper with Mateusz Lisi? Did we not have?
Yes, yeah, I think it was just that you didn't explicitly discuss the zero momentum case. So in the zero momentum case, these things are unrelated. So what happens in your case, I think this will be one of the scalars that you have there, S something, with some index number.
Okay, thanks.
Are there any other questions? So Renann, so are you saying that this theory contains only a finite number of fields?
Yes. Yes. Yeah. In particular for the type 2 case, it just gives you the usual supergravity. But that's not there's nothing new from my side.
I thought you said this contains massless sector and the massless sector as well, right?
Yes.
In some cases.
The bosonic case, yes. But then if you increase the number of supersymmetries, in the heterotic case, there's n equals 1, you have less states, let's say. And then if you go to n equals 2, there's no extra state, it's only massless. Even though you add these tensor deformation, there's only massless states.
Okay, so it's a little surprising. But also, did you say this theory is non-unitary?
Yes, so in the tensionless limit, as Nathan and Matteo showed, you get the spectrum with, or the effective field theory is basically with higher derivatives.
I see.
I can give you an example here. It might make it more clear. So this is the df square plus MUs that Oliver mentioned. So if you analyze this model in terms of the construction I proposed, there are two vector fields. One of them is massless, and the other one is massive. But as I told you, one of them has a different sign in front of the kinetic term, right? So it means there are ghosts. But then if you make a field redefinition, you just introduce this A and B. Here write the action, you get this, and you see this looks like a field strength, and then the equational motion for B is just algebraic, right? So when you plug it back in the action, that's what you get. So this is Young Mills, and this is df squared. And then when you take the tensionless limit, this goes away, and you have this higher derivative theory, df squared. So this is the model that Johansson introduced.
interesting. Okay, so thank you. Are there any questions, comments?
So, sorry,
please.
This is Lionel Mason. I'm just curious as to how it is you get sort of, you know, so you get this peculiar inverted Kober-Nielsen factor in general, and which is as I understood, and but you're saying that in the type 2 case you still get rational answers. Is for the amplitudes, you still get the ordinary gravity. You don't get it sort of
yes, so
something with gamma functions and whatever.
I think this thing is I think it's understood, because in the massive case, what you get here, you don't get these extra poles.
Ah, okay.
So the poles appear only when the mass equals 0.
I mean, of course, looking at the formula like that, you get very nervous about the existence of contours. But then Sebastian Mazera comes along and tells you, you can do it all with twisted cohomology, I think. Yes, I'm not completely certain. And so then when you do that, you get rational answers, not gamma functions in the type 2 case. Is that
yes, that's true. Because you can expand these gammas in terms of this, given these constraints, and then what you get is only a finite number of terms.
I see. Okay. Thank you.
Okay. Are there any questions, comments? So if not, let's thank Renann again. And I think this is the end of the official part of the conference. So as one of the organizers, I'd like to thank all of you for participating in this workshop. And I'm sure you will join us thanking the local organizers, especially Nathan, for setting up this wonderful opportunity during this difficult time. And then, so this is very good. So thank you, Nathan. So we're going to move on to the informal section, but Nathan, would you like to say something?
No, I guess thanks everybody for participating, and I think it went well. I think it's a new experience that hopefully will be repeated. And as I mentioned, next year we're still planning to have strings here in June. So I hope at that time everybody can come here in person. So thanks everybody for all the work you've done.
Okay.
Stop the recording. Maybe we can have the informal discussion. Does that sound right, Eugene?
Okay.
Okay.
Okay. Okay. Let's now